if you work on the blue team, I really want you to, throughout this talk, think about how do I identify malicious RTF documents? And more importantly, what type of techniques and capabilities are available today so that you don't accidentally have some type of ransomware come through and then before you know it, your company has to send all your customers, a letter saying, hey, we lost some PII, right? I don't know if anyone else here has got a couple of those, but I've had several. And then finally, some system hardening techniques. There's quite a few things we can do to really take away a lot of the exploitation surface of RTF. And if you're not on blue team, you're on the other side of the fence, right? So for my red teamers out there, focus on obfuscation techniques. They're very powerful. Sometimes, though, they work like a double-edged sword, meaning that, yeah, it's great you can bypass most detection systems, but for any analyst to really look at this, be like, well, this stands out like a sore thumb, right? Because every layer of protection kind of has its own weakness. And then finally, exploitation techniques. In my opinion, what we'll see here is I think the packager object is probably the best replacement for macros in a way. And we'll see a little bit more of that later. As I mentioned, when you don't know where to go to understand something, you gotta go Google it, right? Get your hands on some specs. So to understand RTF, you must RTFM, so read the freaking manual. There's quite a lot of interesting features about RTF. So this was kind of Microsoft's brainchild back in the day, and I think it's about 30 years old now. So probably, well, it's my age, but probably older than a lot of y'all have been around. There's some really interesting features, right, that I didn't know about, such as the ability to query a database or a flat file. I didn't think you could be able to do that, but that's exposed to the merge functionality. Hyperlinks, I'm sure that was a big wow factor back then. OLE, object linking and embedding. This is pretty important just because it's definitely embedded in the heart of Microsoft, and we'll look at the OLE packager object and how it's abused. Document variables, which I think is pretty cool, and then there's actually even functions as well that will accept parameters inside the spec and be used. Then, of course, on the other side of the fence, there's a bunch of features you would expect out of a rich text format, such as custom fonts, pictures, support for hex and Unicode, and a lot of cool other things. So to talk about it, I hope a lot of us are familiar with HTML, and this is the best way I could kind of contrast this is to think of this as another markup language. So above we can see in HTML we have a simple hello world example, and we include an image tag pointing to a picture of kitty, right? Kitties are good. And then if we wanted to transfer that into what would be the RTF syntax, we'd have we see on the bottom. So HTML predefines their markup with HTML, RTF, big surprise, right? It's still using B for bold. And then finally, where things get a little different is, how things are embedded. So here we would use what are known as object tags. So we have the picture tag, and then we'll have some metadata describing the picture, right? How big is it supposed to be? What's the height? What's the width? And then finally, we would have the encoded data of the picture. So it's actually pretty simple to look at until you actually open one up that Microsoft put out, and there's all these additional meta fields, and everything's all slammed together. Nothing's been beautified for you. It's kind of a mess. So let's play. And we're going to just very quickly build a RTF document from scratch. We'll use an RTF document to perform a SQL query, and then possibly look at some built-in functions. So. And I'm sorry if the picture looks lame. Could have been scarier. Could have did Donald Trump or something. Let me figure out. All right. So we'll, in the spirit of DSU, we'll do this the Halverson way, right? You don't need no fancy text editor, you just need Notepad. So, we know that we need to kind of start off with, a header. Ours is RTF. The one specifies the version number. We'll use B for hello DSU, and we'll just kind of make that the end of our quick example. We'll just name it example.rtf. Good thing I didn't use that name already. Something's already failed. Welcome to my demo. Sorry. One too many of those. Probably should have opened this in WordPad, would have been a lot quicker. All right, so boom, hello DSU, right? Pretty simple. I mentioned that as an interesting feature, you can also query databases. So here's one I pre-built, and I have a Excel file and documents called example data sources, and hopefully I can get that back. All right, there we go. So I use this machine for a lot of testing, so if we just see like a random pop-up, it's because, well, it's work. So, here we can see some fields, first name, last name, etc. And then we go to open this. And we're prompted with the warning, which is great. In the past, this warning may not have been here, but it says, hey, we're about to go ahead and run a query. And we're just going to select star from sheet 1. But the specification does state that, you can actually contact, an actual database somewhere remote if you wanted. And we'll say yes. All right, hey, and we got our data, cool. Just going to open this really quick. I mentioned when you actually open one from Microsoft, let me blow this up. Zoom. All right, hopefully that's a little better, but as we can see, it's a bunch of what almost seems like garbled text, and I'm just really here to just show the select statement and how things could be modified, right? So we're specifying select star from sheet 1, we define, where we want to read it from, and we have some formatting syntax as well. But theoretically, if you were in a kind of a lockdown environment, this could be another way of actually querying some type of data source, right, without some type of native client you may be used to using. So probably more on the I don't want to call it like too much theoretical, but something you'd probably only see in a movie, but it's there, right? The capability is there, which is important to understand. So, trying to flip back here. All right. As far as built-in functions, the only one of interest that I found is really just the time function. So I got that in the lab, just trying to see what I can find. So let's talk about exploitation, right? At this point, we kind of have an understanding of how the format is all laid out, right? And at a high level, it's magic for most of us. But we'll look at some practical magic, if you will. That's like, hey, I think it's something I could use, or I'm sure I've seen that before and I didn't quite recognize it right away. So from an attack path perspective, you have end-day vulnerabilities, right? Things that we already know about. So if you go to ExploitDB today, we'll see things like CVE 2014, 1761. That pertains to an object confusion vulnerability and a list override count field. We'll have CVE 2010 3333, a simple, I shouldn't say simple, but a RTF header stack overflow. These are, even though they're older, you have to understand organizations can't always keep up with patching, right? We just saw, on Twitter in the wild, like a new IIS6 vuln out, right? Or exploit out in the wild. And then when you go to Shodan and see, well, who still uses that? Well, quite a few people still do apparently, right? So don't always try to throw it out the window just because it's older. The other piece is embedded font vulnerabilities. We'll talk a little bit more about that in a little bit. Insecure library loading. For those of you that maybe took a look at the WikiLeaks dump, right? Vault 7 talks about, hey, here's some insecure library loading vulnerabilities in other software. And we'll walk through exactly how those work. And then finally, my favorite, packager objects. You know, you don't really need an actual exploit. You can just take whatever your payload is or whatever maliciousness you want to deliver to somebody, package it up, send it out the door. So here's my CVE fish. You know, I did a lot of fishing here in Madison, so this is probably the best way I can explain it. If you notice, though, he has a lot more fins than normal fish. And if you look at it from like the tail end moving forward, they were kind of like, you know, hey, you would see a couple of well-known CVEs pop up, and then, you know, 2013, 2014, not so much. But if you look at recently, right, you know, over the past couple of years, like, we're seeing more of these. And that's because this is something that's kind of old, right? And I don't know if any of you guys are software developers, but if you've ever had to look at someone's old code, or maybe you have some old code you've written, right, and you had to go back and be like, why did I write it like that, right? There's bound to be, you know, some type of hidden treasure there waiting to be exploited. So I talked about, you know, embedded fonts. So the Duku malware leveraged an O-Day TTF exploit, and the seriousness behind this is just because the font engine lives in the Windows kernel. So, you know, when these type of exploits hit, we're talking kernel level execution. There's a security researcher, Juru, at Google. If you wanted to learn more about that, I would really encourage you to, you know, read his blog, take a look at the work he does. It's quite amazing. The downside to a lot of this, though, is that when you go to embed these type of things inside RTF, the size of your file will go from like this to that. Right? It'll just quickly expand, and you're just like, why do I got a 15 meg RTF file, right? Like, that's not normal. I mentioned insecure library loading, and how it works is when you go to load an executable, start looking at search paths, right? Like, hey, if I need to import something and I need this, you know, DLL called, I don't know, helper DLL, right? Well, I'm going to look at my local directory, and I'm going to look at the system directory. If I can't find it there, I'm going to check some known locations. And what happens is if these if checks aren't put into place, it's very easy for you to just kind of put your own DLL in there, so that when it's opened, it calls whatever your malicious DLL is, and, you know, that gets embedded in the process space and eventually executed. How does this work from, you know, a high-level like attack scenario? So, you know, you're going to get a bunch of malicious emails. We know the classic story. When user gets email, what does user do with email? The user opens it. And then this, inside this email is going to be a link that's going to go to a WebDAV SMB share server that the attacker controls. And since the document's there, when they go to open it, there's also a DLL on that server, a malicious DLL. So essentially, your computer literally reaches out across and says, hey, let me open this remote DLL, and then you have remote code execution. Thankfully, though, I mean, a lot of enterprises are pretty good at locking down their egress traffic. So if if SMBs shut down, it's not going to work. That was my phone. So, no macros. The packager object, I think, is, again, pretty badass. The interesting aspect is it isn't just RTF, right? You can use this in Doc, DocX. It's not just proprietary to RTF, but I mention it because of how you can obfuscate the payloads inside. So we have here our packager DLL. It makes a call to shell WAPI. And its job is to basically try to understand what is the user embedding, right? Is it an executable? Is it a COM, .bat, link? Basically a lot of malicious executable file extensions we're used to seeing and hearing about. And if it is, you're going to get a warning, right? But just, you can't get around that. But if it's not, well, it's just going to let it through and allow the user to click on it like normal. And the beauty of that is if you can find some type of like other attachment that could possibly trigger something, well, you can now embed this in a document and send it to the user so that when it is clicked on, there's no warning. It's, you know, it's instant win for the bad guy. And we'll see a demonstration of that where I take one of Juru's exploits, embed it in a document, open it up, and just blow up a VM. So on top of that, you traditionally, when you embed anything, really, you'll typically see, hey, it's an icon showing that this is like an executable, etc. Well, with RTF, it's really easy to kind of change the appearance of whatever they see. So if you're sizing up, your target, and you understand, hey, me, like I like Counter-Strike, right? So hey, we got this great Counter-Strike meme, and somehow you managed to get me to click on that. I'm sure I will, just because I'm an idiot. And you'll be able to get code execution. As far as the process, just open up Word, find a picture, save it as RTF. You'll go and find the picture object, you just copy it, paste it in your malicious document, ready to rock and roll. The other really important thing about the packager object is that when that is opened, that file technically exists exactly in the user's temp directory. So it's nice because, in a way, if you needed to deliver something and needed to make sure, hey, I need some type of foothold, I need some type of hard-coded address, in a way, right, on the target's PC. Well, I know that if I get them to open this, I'll have my executable sitting exactly at this directory. And it doesn't matter what your payload is. I mean, take any file. I don't know if any of you guys ever had issues at work trying to email a zip file. I work with a lot of malware, so it doesn't really work as well when you want to do it in zip. You just put that in a packager object, it'll go through every email filter, I promise you. Why? Because I checked them all. Because I was just like, hey, I found it interesting, right? It blocks all these other things. How come it can't block this? So I mentioned, here we go. Sorry, I was looking for Juru's demo here. So I mentioned that we have the ability to kind of bypass some of these packager checks and get right to code execution. So I'm going to keep doing this, apparently. Need to just pull up my other VM. Ah, there it is. Coolest background in the world, by the way. Here we have a payload. Now, I haven't changed the image at all. So since RTF doesn't even really know what to do with it, it's just here's a blank little, here's a blank little image. Go ahead and click on it. But we could, if we had wanted to, copied some other picture off the internet, saved it as RTF, copied that tag, put it in, so we've laced it, right? All right, I didn't even get a warning, right? I just got the blue screen to death. Why? I mentioned that the font engine lives in the kernel, so when it goes to execute this POC, well, we're going to get a blue screen. Why? Because all of the execution has been thrown off for this, so it's now in BSOD heaven, and that is the end of that VM for now. Well, there's another word for it, but politically, yeah, it is. So vulnerability discovery. This is an area that's really interesting. I'm teaching a course this weekend, and part of this is over the vulnerability discovery methodology, right? So how do we go about finding bugs in the real world? And I had an opportunity to fuzz the RTF spec for a while, and I found quite a bit. So there's two approaches when you go about doing this. You have what's known as mutation-based, where you take some type of normal RTF document and you start changing fields, right? And you keep opening it in a Word renderer such as Microsoft Office to see, hey, how is it behaving? How is it behaving, right? It's very popular. But then there's another approach, which is known as generation-based fuzzing. And this is the approach I took. Why? Because you could actually waste a lot of time just randomly changing things you don't know about. But if you take the time to study the spec and put together a data model that says, hey, I know that an RTF document has to start with this header. I know that these tags are allowed, and here's how they should be formatted, and start developing test cases to help discover things, you can find quite a bit. So as far as fuzzing tips here, when I opened up the spec, we can see I took out I started looking for the word must, right? And it's crazy because in the RTF spec, there's 100 times you can see the word must there. Like, it must be like this, it must be like that. So as researchers, like, we don't care, right? We're just like, all right, well, what if it's not that? How are you going to react? And we can see here, like with the list ID down at the bottom, there's actually, two popular CVEs related to that, 2012 2539 and 2012 2528. And long story short, you look at, again, we'll look at the list ID. So list ID N, and it says that the list ID cannot be between -1 and -5. So as a researcher, well, we want to know what's going to happen if it's -5, or if it's between -1 and -5, or what if it's -55, 55, 55, right? And so on and so forth, to understand how is our target program going to react to this. So as I mentioned, I went through the RTF spec. I started up 6 fuzzing machines, and this took quite a few months to get through because I don't know about you guys, but when I load Microsoft Office, it's not the fastest thing in the world, right? It's kind of like you when you wake up and you don't have coffee. You're like, maybe I'll go to work today. No. What I found, though, in the long run, 500 crashes, 6 of them unique. And to demonstrate what this process looks like, and for those of you that are taking my class, you'll definitely have an opportunity to get hands-on with this approach. So I chose Peach, great fuzzing framework, and I've built I created a data model of this specification. I'll show a little bit of that here as well. So I'll just start running this. So the first thing that happens is, well, it wants to make sure that it can open it and everything is going to be recognized properly. So, all right, so this happened at DerbyCon, and I got super excited because we didn't even get a chance to see it open, right? It just says, hey, something happened, and we already got a crash. Now, as an attacker, that should make you as a vulnerability researcher, that's, this is what we want. Yellow is gold, right? But it's not gold when it's on the first try. And I went through and I saw it actually happened to be because of some licensing issue. Speaking to what this kind of looks like, so, here's my data model, RTF file tables, and I just start taking things from the spec and defining, here's what it looks like, here's how it should be formatted, so that when I go to fuzz that, I know which fields I should be focusing on. And I can be very granular on exactly which fields I want to fuzz. So some food for thought for those of you thinking about going down this path. All right, my focus was on Microsoft Office for Windows, but what about other platforms? I use their mobile app, right? So maybe on a different platform, as code is ported to different architectures, how is it still going to handle this? Think about cloud-based document services, right? So Google Docs, that's really popular. What could we possibly find there? And, just some other word processors, Text Wrangler, Corel, WordPerfect. That was like the first word processor I remember using. So obfuscation, as I mentioned in the beginning, this is where I spent most of my time initially, was just seeing how can I take something and make it look completely different, right? And deliver it to our target, and they don't know. So we're going to look at some really common obfuscation techniques that exist today. And surprisingly, first one's going to be file extension tampering. So last year, I went and grabbed pretty much as many RTF docs as I could. I got over 1,000 unique ones. And surprisingly, most of them had .doc extensions. So even though the header would show RTF, if you open it up in a text editor, it still showed .doc. 100 of them were actually RTF. Less than 10 tried docx, which isn't going to work, and then 300 had like just some other random extensions. The beauty here is well, that made me wonder, what else could we name this as, right? So surprisingly, I found that dot works for template, dot HTML, HTML template, WBK workbook, dot whiz for a wizard. And when it's delivered, it changes the icon they see. So for pen testers out there, as you continue to try other things, put this here in your bag of tricks, right? Because as enterprises get better at security awareness and saying, don't click the link, don't open the attachment, don't do this, just leave your computer shut down, you got to keep trying new stuff. Magic file tampering. So in our example, we used RTF and a number to express the version. Well, Microsoft Office only requires \RT. That is the minimum. So we could actually go back, modify that file, take away the F1, open it up again, and it's going to work. However, if you're using like WordPad or a different word reader, that's not required. A very classic evasion mixed case. So I know for those of you in the programs here, as you go through some of your labs, you can see you can get past some filters by just changing the case. Same thing exists here. I mentioned RTF supports different encodings. So for those of you familiar with like URL encoding on the left, we know capital A is %41. If that was double URL encoded, %2541. In the Office world, or for RTF anyhow, in the specification, we could take Unicode, so \U0041, and then if you want to use hex escaping, instead of like an OX, you would use \single-tick. So from an analyst perspective, as you guys look at documents, kind of be aware of these things, right? If you have to open it up and you're curious. So let's take a look at a pretty good example here. Here's a classic malicious document, and again, with the lighting, probably not the best choice of colors, I agree. But I'm hoping you can still see where some things stand out here as malicious. So starting in the upper left-hand corner, we can see an alternative header being used already, RTF VPN. It still works, but it should stand out as a red flag. Why? It should just say RTF. We see some hex encoding, so the \single-ticks. Looks like it's down several lines here on the right. You can see FALT, \single-tick, 82, so on and so forth. When you see encoding, it doesn't mean immediately that it's malicious. There are legitimate reasons why that's available, but it's something to be mindful of. And then, we see some things down at the bottom that are just tacked on at the end to try to throw off a parser. Another evasion we see is what's known as bin substitution. So I mentioned with the packager object, it's going to format it as a byte stream. And what we have the ability to do here is say, I want these bytes to be represented as binary. The caveat here is that this syntax only works in Microsoft Office. So for those of you playing with this, you'll see that when you go to open up in WordPad, maybe because you didn't have Office installed in your environment, it's not going to work. Probably one of the most simple and effective evasion techniques, white space. And we'll see how that works later when we try to bypass RTF scan. It's a RTF document analyzer. So use this to chunk up your payloads, right? So that whatever signature is scanning that, it can't see that, we see the traditional MZ header because it's, an embedded executable. Fictitious control words. So to me, I think this is probably, again, the biggest double-edged sword. The best part is, yes, it will bypass a lot of detections, but once you go against an analyst who has maybe wrote some custom rules, they'll be able to spot this very easy. So the RTF spec states that if an unknown control word is preceded by a \*, then it starts in an ignorable destination group. So literally what this means, and you can see like random up there, is we have the ability to create our own control words, right? Or define our own syntax, because if we want to write our own RTF parser, maybe we want a cool rule that says like, hey, this is our, this is our headshot rule, or our headshot tag, I'm sorry. And I want my reader to be able to take this data and do something with it. Because when Microsoft made this, they wanted to make sure it's portable, right? I should be able to share this with you, and you should be able to extend it as you please. So there are a couple of AVs that I've seen that are actually pretty good at catching this from a heuristics point of view, but it's still very effective. So here's just an example. Oh, sorry. Here's just a simple example in the left-hand corner. We define a hello tag, and we give it the value world. If we go to run that in Office, it's not going to know what to do with that, because that's not one of the defined words, if you will. So I mentioned bin and white space evasions earlier. So in the upper left-hand corner, we see that they've embedded some type of object, but they started off with a bin word, and they use 0. Well, it states that the number is supposed to specify how many bytes after should be treated as binary data, but they use 0. So effectively, we're not doing anything here. It's just another way of just trying to pad and throw off a parser to so that it doesn't quite recognize what's being used. And then down here at the bottom, we see the white space evasion. Typically, when Office is done embedding something for you, it kind of formats it nicely, so you get like a nice string. But here, we see a new line entered after every single character entered. And yes, that's going to be very effective, believe it or not. And we'll see so later. All right, so RTF scan. Actually, let me just get to it. Let me blow this up just so y'all can see that. Let's go mega font. Whoa, okay. Too much. Way too much. This might be better. I tell you what. Gonna have to kind of work with me here. So we're gonna run this. We're gonna run this tool RTF scan on just a simple RTF document embedded with a malicious DLL. We'll use the scan parameter to see, hey, like, what do you see? All right. So we can quickly see here, hey, it seems to be malicious, right? Now the question is, like, can we take the techniques we just learned to throw this heuristic piece off? So we'll just go and open that up. I'm just going to go jump to the object tag. So here's our embedded object. And, I mentioned, first things first. This is pretty effective to start. There's some other things we can do. We can create some fictitious control words. Hi, Mom, in case you're watching at work. And just so she gets the point. Just start throwing this in, wherever we can, right? But, I'm just randomly picking, looking, throwing stuff out here. I don't know. We'll see where we're at, right? We'll go to scan it again. All right. So we've succeeded already, right? We went from, whoa, hey, this looks, pretty scary. I wouldn't touch it, to now we're not, we don't see anything, really kind of wrong with this. And, what happens here is as the reader goes to open this, it's going to ignore these tags, right? So it's going to, first it's going to combine all the white space, and it's going to start ignoring all these made-up tags we just, inserted. And it's like, just ignore that, but we'll keep parsing right along. And, effectively, The payload still works. We can open this and still see the DLLs there, and then everything works. All right, for my blue team friends. Because again, when I started my career in security, it was on the blue team, so I definitely feel for y'all. As far as those of you that have the opportunity to write rules or that are in charge of like intrusion detection systems, here's what you need to focus on. File extensions. For one, I would really just stop using RTF altogether, right? Maybe allow just docx. Look for malformed file headers. And this is going to require you to change what are known as magic file numbers, right? So the first couple bytes of a file that help define what it is. Normally, people look for open curly brace \RTF. Well, you need to tune that down to just RT. Look for embedded objects, so object data tags, and look for unknown RTF tags. There's some special cases though that you should be aware of when you kind of go about embedding things. The object class tag that we see here on the right-hand side, that's not actually required. It's just useful metadata. Be on the lookout for encoding techniques, and especially mixed cases if they are using the object class name. And then the biggest heuristic thing, or the biggest thing to key on of all, the generator tag. I'm sorry, but obvious is obvious, right? If you're playing Counter-Strike, you go through, you're the bad guy, just chill there by the plant. Chances are I'm going to shoot you. Why? You're trying to hide behind a plant. It's very obvious. It stands out. So look for this tag inside the generator tag. Typically, this means that it came from WordPad. As far as system hardening, so you can actually go find the packager CLSID in Windows and set the Office kill bit for that, so that, hey, even if somehow they manage to get by your defenses, when they go to use that, it just isn't going to work, right? Update your executable extensions. We saw in the packager object piece, like what file extensions it includes by default. Well, you have the ability to expand upon that list. So just think, what are some other things we should be looking at, and make sure that that's accounted for. And then finally, change back the RTF file extension association. Don't use Word, have them bring it up in WordPad, right? So definitely quite a few different ways that you can just make some small changes to your system, so that in the event it does get past your detection controls, you have something to fall back on. As far as analysis tools, this is all I could think of as far as what's been beneficial in the field. So Didier Stevens has a really cool tool out called RTF dump. It'll help you, take a look at, how the document's formatted, do some beautifying, and help you spot anomalies. There's the de facto RTF object from Decklage. FishMeat has a pretty cool PS parser. And what this does is it really just focuses on embedded content and giving you information about that. And then also there's RTF scan. Don't throw it out the window just because you saw it didn't work right. I mean, there's a reason we have these tools. They're not all going to be perfect. So to kind of recap for the blue team, again, update your magic file header for RTF, scrutinize generator tags, focused on required parameters first, look out for .wiz and .workbook. I don't think I've ever seen that ever. And wow, that is very unprofessional. And finally, disable packager objects. And then for my red team friends, take advantage of obfuscation techniques, trade warning signs. I've heard horror stories about where, hey, they have macros disabled. How are we supposed to get around this? Because phishing is a very easy way to compromise any organization or person. Try switching things up, saving it as a different file type extension, and last but not least, fuzz the hell out of RTF. So with that, I guess I'll just kind of open up really quick for questions if there's any. Does anyone want to know who called? I'll tell you. I don't know. Raj. Okay, so the question I heard was how do you go about analyzing so many crashes, and it starts with the crash minimization, right? So yeah, we may have a RTF file that's say 1,000 bytes, right? And it's good that it crashes, but as we keep subtracting bytes and rerunning it, what is the minimum test case we can find that creates that? And then the other piece to it is looking at what part of the code is affected, right? Is there a particular routine that I see that all these crashes are happening in? If it is, well, it's all still the same crash. I'm sorry, it's not quite unique anymore, right? Just because you had some vulnerable function that you saw your test case die in doesn't mean that they're all unique. It just means that there's some type of vulnerability here, and you have to narrow down, what's the smallest proof of concept you can put together. Thank you. Good question. DSU students in the back? I'll leave you alone at CCDC? No, I'm kidding. No, that's not happening. Well, hey, guys, no pressure. I'm gonna be here all weekend, and if you got something on your mind, feel free to talk to me. Be glad to hear your thoughts. Otherwise, big thanks to the attendees here. I'm really honored to be in your presence today. Thank you, DakotaCon organizers. I'm rocking the first shirt because I've came to this one since day one, and I intend to until I don't know, whenever, right?
Who designed that shirt?
So I helped with the logo stuff. Emily Robinson, she was a designer student here. Yep.
You were the big seller.
I did try to sell it. I did. I thought it was awesome. So anyhow, thank you all for your time. No questions, Agent Fields?
No, I mean, when you're presenting.
Oh,
Do you like to
I'll
face around?
stay there.
Okay. If that's the case, you don't actually have to use
Okay. Uh, sound like it was working. Hello, my name is Tommy Morris, and I am a professor of computer engineering from University of Alabama in Huntsville. And I'm here today to talk to you about virtualizing industrial control systems for, title says virtualizing industrial control system test beds for cybersecurity research, but it's really also shifting into for cybersecurity education as we do more and more of this. I came from Huntsville, Alabama, and you might wonder why someone came so far to come to DakotaCon. The answer is I see Dakota State faculty all over the country as I travel to go to project meetings, and I've been on so many different project teams with Dakota State. I wanted to come see it for myself. Dakota State is a very impressive place. You have a very thorough cybersecurity set of cybersecurity degrees here, and so I really just wanted to come and hope a little bit of it rubs off on me while I'm here. So this work is about these virtual SCADA test beds. It's done with two PhD students, Rashab Das and Thiago Alves, both at University of Alabama in Huntsville. First, I wanted to talk about what is a industrial control system, or what is SCADA. So SCADA stands for supervisory control and data acquisition. It's a lot to say, that's why we say SCADA, I think. But basically, industrial control systems, SCADA, these are systems that you find in a lot of different industrial applications to basically monitor and control. In this case, I've got pictures of a small gas pipeline from my lab, a water treatment plant from the lab, and a storage tank, a water storage tank in this case. You also find SCADA in factory automation. You find SCADA in the electric power system. It's basically all over the place. And what SCADA is sensors that are monitoring physical systems, and then actuators. Those sensors and actuators to control that physical system are connected to a computer that's running a program to basically monitor and control that system. And then usually SCADA is connected to a network, and across that network will be what's called a human-machine interface, where an operator will watch over the system, intercede from time to time, take control, and basically operate the system safely to provide some resource for you, like electricity or gas, or to build something in a factory. Because they're networked, they're actually getting more and more connected. They're becoming connected to companies' enterprises, and that puts them at risk for intrusion. And so hackers can get in and start to take control of these systems. This morning in the keynote we saw someone pull up shodan.io. You can go on Shodan and search for industrial control system protocols and find systems directly connected to the internet. And so there's a real need to protect these systems because they provide a lot of the critical infrastructure for our country. So at UAH, I run a lab called the SCADA Security Laboratory, and in that lab we have these reference systems. They're kind of small. The gas pipeline, for instance, has a pump underneath that you can't see. I'll show on the next slide. It has a solenoid to open and close a valve. So I have two ways I can control it: turning on and off the pump, and opening and closing the valve via the solenoid. And then I have one sensor which is measuring pressure. The water treatment tank is similar. Some pumps to pump water, move them around. Some sensors to know where the water is. Same thing with the storage tank. These are small-scale physical systems that what we can do with them, we have the real physical system, plus underneath we have commercial programmable logic controllers, and we're connected to a network with commercial HMI, so we can do cyber attacks against these systems and then look at the impact of those, and then we can examine different security controls and intrusion detection to look at whether or not those research ideas work, basically. The other part of the lab, we have these HMIs. So HMI is a human-machine interface. It's basically a GUI. An operator can watch over the system, see the current state, and then interact with the system as needed. And then this last picture on the bottom right is actually down below the gas pipeline, just looking in the cabinet below, just so you can see the pump there in the foreground. In the back, there's actually a PLC. PLCs are nothing more than little, usually they're 16-bit microcontrollers connected to some digital I/O and some analog I/O. That microcontroller will run, maybe it runs a real-time operating. Runs its little ladder logic, which is the program that an engineer will write, and then does its communication and goes back to sleep. Because in 2008, when I started doing this research, this is the kind of systems we had. We made a lot of hay, wrote a lot of papers about cybersecurity for these things, but as we went along, they got too small. The world's moving to big data. These are representative on a small scale, but for instance, a gas pipeline with one pump and one valve really isn't representative of a real gas pipeline. There's going to be hundreds of pumps in series over maybe 1,000 miles. For instance, the Dakota Access Pipeline, that's going to move oil from Dakota down to Texas. So that's going to be a very long pipe moving a lot of flow across many pumps. And so on and so forth. So we wanted a bigger system to do our research on. And so but we can't afford it. There's, also, we are lucky we have these systems. There's a lot of other researchers that would like to do this research, but they don't have access. And so actually one of the genesises, well, I'll tell you, the real genesis of us virtualizing these systems was laziness. My office was a mile away from my lab at one point, and so I started virtualizing them so I didn't have to go to the lab, because I was writing programs, and I didn't want to walk across campus. So the very first virtualization, which was all kind of text-based with some networks across some VMs, was just so I didn't have to go to the lab. I was writing some intrusion detection stuff. I tested it out fully. It worked in my office before I ever went over to the lab, and actually the virtualization was good because it worked in the lab the first time as well. So these systems are too small. They cost anywhere between $5,000 to $20,000 each, depending on how complicated you get. So it's hard for just a lot of universities to have access to them. It's also very difficult for me to give you access over the internet. I could hook my network up to a VPN or something like that, but you wouldn't be able to see it. And so if you had some physical impact, you would only know data-wise. You wouldn't be able to. Sometimes it's kind of cool to hear the pressure growing, and that's all instructive as well. And so between wanting to make them bigger and give other people access to them, we decided we needed to virtualize these things and give them away. And so what we've done is we're going to talk about 3 different virtual SCADA systems that we created, and show you how we broke it down and how we virtualized it, and then show you some results graphically, comparing a real system to a virtual system, and then I'll give you a quick demo at the end. So what is in a SCADA system? We break a SCADA system into 5 basic pieces, and so you see on the far left there a physical system. So that's the gas pipeline from our lab. It's basically got some pipe, some valves I already mentioned, a pump. That system, the actuators and the sensors connect via wires to digital I/O on the middle thing, which is the programmable logic controller. So there's some sort of wire bridge or wires between the two. We actually count that as one of our 5 basic components, is those wires. Then the programmable logic controller. And then that programmable logic controller usually is connected to a network. There's a lot of different we'll call them less popular communication protocols. There's Modbus, DMP3, Fieldbus, Profinet. They're all dedicated for this industry, and so you don't hear about them if you don't work in kind of the SCADA area or if you're not a hacker trying to break into these systems. And so that network there is another major piece, and then finally the human-machine interface. In a real SCADA system, you'll also find out near the human-machine interface that maybe a historian to collect some data, and we don't have a historian in our virtual SCADA system. So if we take that gas pipeline and we want to virtualize it, first we need to understand what's in each component. So I wanted to walk you through what each of these components has. So I already talked about kind of the basics of this, but basically the physical system in the gas pipeline, it's 1-inch pipe with 4 90-degree bends, 2 T-joints, some sensors and actuators, right? I go through all of that because that's the level of fidelity we actually ended up virtualizing the system to. We actually modeled the 90-degree pipe bends and the T-joints and et cetera. When we first started this, we actually went into the lab, and when you turn this gas pipeline on, the pressure goes from 0 up to some set point. We just captured data, did a curve fit on that rising edge, and modeled that with a simple equation in Python, and then we did another curve fit for the falling edge, and we called it a day for our model. But the model started to break down when you were running the system away from where you did the curve fit. So we decided we needed a higher fidelity physical system model. So I'll tell you how we did that in a second, but part of doing that was actually understanding all of the specifics of that pipeline and how it's interconnected. What is a wire bridge? Basically, the sensors are generally, if you have a pressure sensor, that's just an analog value that's being read, pressure coming across an analog single wire, goes into an A to D converter, converts it into a 16-bit number. And then usually the control back is just going to be, a lot of times it'll be a 24-volt signal, 0 or 24 volts for off and on, 0's off, 24's on, etc. And so you'll see that's a picture of an actual wire bridge from underneath one of our cabinets. That's what they look like, just a bunch of wires that end up going into the I/O of the PLC. Programmable logic controllers, they're just, as I mentioned before, microcontrollers with the I/O. They run a user program. The user program, there's actually 5 different languages that are standardized by IEC, but usually they're running something called ladder logic, which is a very simple programming language designed for engineers that don't like to program, basically. And it's an older language that was designed back before all of the engineers were taking C and other programming classes in school as well. So in our case, our lab came with Siemens microcontrollers, and those are great. They're very, very popular in the market. There's a lot of vulnerabilities out there that you can go and download and metasploit and then attack the system, so that's nice. But actually, when it goes to actually trying to defend it, they're a black box. Siemens owns everything inside. So I know the I/O, I know the protocol, so I can do like a network-borne attack, but if I want to defend it, all of my defense has to be from the outside. So another thing that we wanted to do was be able to get inside. That's always been another dream of mine, get inside the PLC, but without butting up to Siemens or Allen Bradley or someone like that, which I'd love to do, but I haven't achieved yet. I needed my own PLC. So we made the OpenPLC as well. And the OpenPLC is at this website, openplcproject.net. You can download, OpenPLC comes with a full development environment. It's a soft PLC. I'm getting ahead of my slides though. I'll move on. It's actually recognized in a lot of blogs. We've got 3 companies that are now using OpenPLC in their platforms. So it's really taking off on its own. And when we virtualize, we actually use the OpenPLC because it's a handy platform both for research and for virtualization. I mentioned it has a development environment and it supports, there's these 5 standardized languages. The OpenPLC supports all 5 of those in its development environment. OpenPLC right now speaks Modbus, which is pretty much, it's an open standard, the most popular industrial control system protocol. We actually, because it's an open platform, something really nice happened. Some people are starting to contribute to OpenPLC, and so just recently, some students from Johns Hopkins added DNP3. So it's not on the slide, but now we have DNP3 support as well. And we're working on adding Profinet. Profinet is a closed protocol, so it's the intellectual property of Siemens. We're going to add that in the lab. We're not going to put it on the website. It'll be available by request to other researchers, but not given to the world for free. So the OpenPLC I mentioned is a soft PLC. It runs on a lot of different platforms. It started on our own individual hardware, but now it runs on Raspberry Pi. This UniPi is a company that sells basically an extension to Raspberry Pi. So when you buy UniPi now, you can click down and have OpenPLC automatically installed on your Pi when it ships. Pi Extend, similar. It runs on this ESP8266 platform, which is like a $5 Wi-Fi plus 32-bit microcontroller. Very nice platform. Arduino. And then the soft versions also run in Windows and Linux. And then, not shown on this, we have a prototype in our lab of a small platform that we developed ourselves with just 4 inputs and outputs that we're looking at providing to students for lab type work as well. OpenPLC, PLCs I mentioned also have a human machine interface. OpenPLC has SCADA BR, which is an HMI editor and PLC. That HMI speaks Modbus TCP. You get the supervisory control, and then the PLC periodically will poll the PLC. The HMI will periodically poll the PLC and grab the status and send control information. So those are kind of a little more in depth on what the pieces are. So how did we virtualize our gas pipeline? The gas pipeline was the first one we did. So what we did, we had these same 5 pieces I showed before. And so is that, oh, it's not up there. There we go. I have 2 pictures of the screen. Y'all only have 1. So what we did basically is, so for the physical system, we used MATLAB Simulink and made a MATLAB Simulink model of the system. We replaced the wire bridge and the analog and digital I/O. We found a way to actually create little UDP sockets between individual points or variables inside MATLAB Simulink and our PLC. So we basically simulate the wires with UDP packets on a private network that's not on that same SCADA network. It's back in the background so that so it doesn't interfere with the true traffic from the system. We used OpenPLC on the physical system, and then the soft version of OpenPLC running in a VM for our virtual PLC. And then for the network piece, in a real system, you have a real switch, a local area network. In our virtual one, it's using a network provided by VMware or VirtualBox. We've used this on VirtualBox, VMware, and KVM. And actually, you can, instead of using that virtual network, if you want, you can connect the virtual PLC to a real switch and then connect up to an HMI across a real network if you want. And then the HMI actually is just a piece of software, so it doesn't change between the virtual system and the non-virtual. So I think I just talked through this animation, so let me skip that. So the physical system, basically in MATLAB, this is the high-level diagram of the physical system, and then if you click on that middle box that says SCADA Lab, actually what you see on here is just communication, and then that middle box expands to the actual gas pipeline. So it's got all the pipes, it's got valves, all of the the pump, etc., is all modeled in there in MATLAB Simulink. I'm not going to point at anything and tell you what it is. The only thing I will say is, something you might not think about when you're modeling a pipeline is the one in the lab pumps air into the pipe and keeps it at a certain pressure. Well, we had to have a source for air. It's just here, we don't think about it. So at the very bottom there, it took us a while to think, where do we get the air? So we made a big giant reservoir. That's kind of what a room is anyway. It's a reservoir full of air. And so we pump from that modeled reservoir. Anyway, so we did that, and I'll go through some slides showing you how the virtual compares to the real system in a second. We also have virtualized a few more systems. So we had the water storage tank. We've now virtualized that. Outside of this one slide that says we did virtualize it, I'm not going to prove it to you today, but we virtualized that, and then we've grown it into the gas pipeline. We've grown into a much larger system. I'll show at the end. So we did some testing. We wanted to make sure that our virtual pipeline matched a real one. So if we're going to use this for research, it needs to actually be reflective of a real system. So we wanted to look at the real-time response. PLCs are often real-time, meaning that they need to wake up and do something in a predictable time. So for instance, maybe they need to wake up every 50 milliseconds, run their little ladder logic program, and make sure the system is in a safe state, and then go back to sleep, okay? Well, every 50 milliseconds, not 52, not 54, okay? And then we look at the pressure curve and the falling pressure curve, and then we did actually a man-in-the-middle attack to look at both the virtual and real, how they compare. So on the real-time response, we're not perfect. You can see that from the graph. The real is on the right, so the physical system running with the OpenPLC, and the virtual is on the left. And so what you see is the real PLC running on a Raspberry Pi. There is a Linux operating system, but it's not doing very much. And so we have a very tight curve around 50 milliseconds. We're waking up every 50 milliseconds. And there's not much variation around 50. You can see on the virtual one, now we're running in a VM on a Windows host. And so you see these spikes all along the way, where a lot of time it is waking up right around 50, but there's a lot of spikes there above and below 50. And that actually has to do with the fact that the VM is not running native on the machine. It's actually, I guess that's a type 2 VM, is that right? Where it's actually running as a process on the machine. And so we're kind of beholden to the scheduler of the host OS. And so sometimes we just don't wake up when we want to. And so that's a limitation of our virtual process. You can see some of the bigger spikes are plus or minus 4 milliseconds, which could be bad. It really is application specific. One of the questions I've been asking my PhD students a lot is it good enough or not? And in the discussion we have about that all the time, it comes down to, well, it depends on what you want to do with it. If you're just wanting to see pressure trends and whether or not a pipe blows up eventually because pressure rose above some unstable state, you will get there with this, even on the left, with that kind of responsiveness. It's just that you might be a few milliseconds. You might notice that it blows up a few milliseconds later than you would have if you were using a real system. But if you're trying to train a machine learning algorithm with very tight timing, then that could become a problem. Oops, I went the wrong way. So then the rising curve and the falling curve, those are a much better match. You will see that the two curves are not exactly the same. And we did some investigation. Why are the two curves not the same? That's actually a MATLAB Simulink issue. So MATLAB Simulink basically doesn't model air resistance. When you're pushing air into a pipe, there's already pressure there. And so there's some pushback from the air that's already there. Even when you're pushing out into an empty room, there is a set pressure, and there's some pushback. MATLAB Simulank's not modeling that, and so you see that discrepancy in the curve. And again, we had the discussion, what's good enough? We really feel like this is good enough for that particular case. And then finally, we looked at just an individual attack. This is an attack where we did a man in the middle between the HMI and the PLC. And the man in the middle is just done with EtterCap. We had an EtterCap script that just added 10 psi to the pressure, so we did look down inside the payload. We knew what bytes that pressure was. We added 10 psi to that and sent it on its merry way. And so on the left, you have the real system with a man-in-the-middle attack, and on the right, you have the virtual system with a man-in-the-middle attack, and you can see the behavior is very similar. You do see some differences in the shapes of the curve, but that really comes back to this previous slide with the slight differences in the rising and falling pressure. Otherwise, we have a very similar shape. The one on the left ran a little bit longer, and so you have, well, it just has this extra rise, but that's not really an artifact of poor simulation. It's just something we did a little more than we did on the right. But then what's interesting, though, is we do see basically the timing is very, very similar. And then we like this line here. Right before 3, that's when we turned on our man-in-the-middle attack, and that's an artifact of turning it on. We changed the pressure at a very high rate. It went basically from a low value to a high value very, very quickly. That violates the laws of physics. So if you were doing some sort of detection, you can look at the rate of change of pressure as a detection in an IDS. Well, that's in the simulated version as well. So you would be able to test out that type of security control in the simulated version. So then, one of our original goals was not to model the systems we already have in the lab. That's nice. But to build bigger systems, because we want bigger systems for our own research. So we did. We built a virtual 15-kilometer gas pipeline. We tried this twice. The first time we did it, I did it with one group of students, and we got a working 15-kilometer pipeline with 5 pump stations, kind of like drawn here. And then I hired this grad student who happened to work for 2 years at a shipping terminal working on a pipeline that moved liquid propane and liquid butane from basically the shipping terminal to a network of tanks. And he looked at our model and said, we did it all wrong. So we did it again. This guy, because he had experience, knew that you needed not one valve at each location, but 3 valves, a manual valve, a remotely operated valve, and I don't even remember the third one right now. But so we redid the whole thing, and so now we have a working 15-kilometer gas pipeline. It actually will move cargo, is what he called it. So basically a shipload of butane from the tank on the right to the tank on the left. You can also, before you move something, it turns out you have to recirculate in the pipe to cool it down to get the pipe to the right temperature. So it has a recirculation mode, and then there's actually a manual mode to allow you to move from the tank on the left back to the tank on the right. Or excuse me, the tank on the right back to the tank on the left. And I'll show you a demo of that one in just a second. But what are we doing next? We've just picked up in the last 6 months several projects. So we have an NSF CyberCore capacity grant to actually start developing these for other engineering disciplines. So I hooked up with professors from chemical engineering, civil engineering, mechanical engineering, and I'm doing the electrical one. To come up with designs that students in those disciplines can learn on to learn about cybersecurity for physical systems in a system that's relevant to them. So chemical engineering, we're doing a distillation tower. We have students in chemical engineering under the supervision of a chemical engineering professor modeling the distillation tower, and then my students and I are providing the framework, and then we'll go in and teach with that system in that class. We're doing a mass damper, which is a big weight on top of a tall building to counteract wind effects on a building, a robotic arm in mechanical engineering, and then an electric generator for the electrical engineers. And then we just actually won a grant from NSA to actually take the lab, the ones that we just talked about in this talk, and develop 7 labs and accompanying lectures that will be provided around the nation for students to learn on. And the proposal we wrote said that we were going to provide those on servers to other universities. We're still trying to figure out, we have the servers and we may do it that way, but there's some talk that it might be a single university hosting lots of different things, so I'm not exactly sure how to be deployed yet. And then we are doing for the Army Corps of Engineers a virtual test bed for a high-performance computer cooling system, so they have either water cooling or lots of airflow into these things to keep them cool, and that's kind of critical infrastructure to those computers. If you take out the cooling system, they have to shut down the computer. And then finally, we have a project with Entergy that we're looking at detecting cyber attacks against relays in an electric transmission substation. That one's using Splunk, but it's kind of based on some work we've done before. Real quickly, I want to just show a demo. I've got VNC open, so this is running back at UAH. And so you can see the system's up and running right now. At Station 1, it'll turn on and off over time as the pressure builds up there. The later stations are, oh, great. I think I need to take my, one second. That's what I'm trying to do, get back to, yeah, I won't go, Control Alt Shift F. There you go. So here it is running. So you can see that, you know, this is the HMI you're seeing right now. And so you can see the pressure values are changing, the flow rate is changing along the way. And so right now, Station 1 is off, so it's not moving any flow, then it turns on and it starts flowing. That's just inside Station 1. Each of these stations has a PLC that's running that particular station, so it's monitoring what's happening at that station and turning on and off the pump to keep the whole thing flowing. Each station has a separate screen that you can pull up to change settings, make different, you know, monitor more closely. And then, so each of these runs in an open PLC VM. Not very interesting. There's just VM there running a process, but I thought I'd show you. There's 5 of those. And then just, I'm not going to do any attacks, but you can also run Wireshark. So if I start Wireshark real quickly, you'll see lots of Modbus TCP transactions going across. So basically, Modbus going from each of those PLCs back to that one HMI. And so then we can do things like man-in-the-middle attacks. We can do TCP session hijacking and send commands in, things like that, against these systems. And so that is, in a nutshell, virtualizing industrial control systems. And I went over time, but if anyone has any questions, please feel free. All right, thank you. Oh, yes, sir.
What are the computational requirements for hosting that media with all this process? What kind of hardware do you need in order to do this?
We run this. This is running on a PC that's just a standard. It's got about 16 gig of memory, but it's actually not, you know, super beefy. It's one processor. I don't know how many cores that processor has. These PLCs are all very lightweight. Trying to model a real PLC, they don't have very much memory or processing power. Actually, the main horsepower is there's one copy of MATLAB Simulink running for the entire physical system, so it takes the most resources. But all of this runs on one PC. We have another system in our lab that's designed to run MATLAB Simulink in real time for much beefier things, but we were kind of surprised. We run them on there, but we don't need them yet, or need that system yet. It's called an Opal RT. So, any other questions? All right. Well, hopefully around August we'll have those 7 labs out, and schools will start to pick them up, and hopefully Dakota State will start using it. Thank you.
All right. Good? You guys hear me okay? All right. Hi, my name is Dave Au. That's loud. Is that too loud? Better? Okay. Hey, my name is Dave Au. I am a penetration tester with PSC. It's a payment software company. It's a company out of Campbell, California. This is titled, obviously, I got this hacking degree from DSU, now what? The company I work for, PSC, specializes in the payment industry, and we deal with clients that primarily, work in payment cards and such. So, a little bit about me. I'm from right up the road. I'm from Arlington, about 24 miles away. Graduated in '98. I got a degree from SDSU in 2003. We'll skip, but I worked for a few years and then ended up getting another degree from DSU in 2010. My first security job right out of school was as an information security analyst for a company down south in Baton Rouge, Louisiana. Did that for about 5 years, and now I am working as a penetration tester. I get to hack full time. I've been doing that for a little over a year now. So I wanted to talk about penetration testing, what it is and what it is not. There's something going on in the industry where companies will take a vulnerability scan, do some false positive testing or manual verification, write reports, and deliver that as a penetration test. My definition of penetration test is much different from that. A real pen test will include some sort of success criteria. That success criteria might be trying to get to exfiltrate data, trying to get to secured environments, that sort of thing. So all penetration tests will include some of these things, right? So reconnaissance, learning as much as you can about the organization as possible. Followed by some enumeration, figuring out what's on the network infrastructure, what devices are out there, what ports are open, what services are available, followed by identification of vulnerabilities. What can you exploit? The next couple phases, exploitation, post-exploitation, that's where you're trying to get to those to that success criteria, whatever that criteria is that you set up with the client during the pen test. And then as far as like the post-exploitation, that's vertical and lateral move around the network, exfiltrating data, getting to those secure environments, what have you, followed by the long, painful report writing process. It's kind of interesting. I was having a conversation with someone once, and they referred to pen testing as an art form, and the pen tester as an artist, right? No two networks are the same. They're all different. Hacks are elaborate, crazy, and a pen tester is really doing a lot of things that a machine can't do. Right? So there's a very manual, thoughtful process in performing a pen test. So I mentioned that I work for PSC. We specialize in the payment card industry. So what's PCI? PCI stands for Payment Card Industry. The DSS, the Payment Card Industry Data Security Standard, it's this set of standards designed to ensure that all companies that accept, process, store, or transmit credit card information maintain a secure environment. What does that mean? This is an oversimplified network diagram, but you've got corp.com. That's the corporate domain. That's where the regular domain users work. That's where even the IT folks are, right? And then in a PCI environment, you have something called the CDE, what is below that red line right there. The CDE stands for Cardholder Data Environment. That is where those credit cards are being processed, stored, transmitted, and whatnot. So a secure PCI environment will ensure that that CDE is not accessible except through very specific means. Okay, so if Bob wants to get to that database, there should be no direct route for Bob to get to that database. Okay, the only way for Bob to get that database is to actually go through that blue box right there. That blue box is called the jump box. That jump box, you can think of it as the gateway into the CDE. Okay, so Bob's going to authenticate to that jump box. Username, password, maybe RSA token, something along those lines for multi-factor authentication. And then once he's successfully authenticated to that jump box, then he has access to the database, right, into the CDE. And keep in mind, again, this is a very simplified way. The jump box method is one method. It's one that I see quite often, but there are other ways of securely accessing that secure environment. So why are PCI pen tests different? And I was talking about that success criteria. For us doing these pen tests, that success criteria is getting those credit card numbers. It's getting to the CDE, okay? So if, let's say I get domain admin in the first day, I have the keys to the castle, to the corporate domain, but if I can't get to the CDE, I didn't meet my success criteria, okay? So, think of it this way. In a well-designed PCI environment, the compromise of that corporate network should not affect the security of the CDE. So that CDE should be ultra-hardened. There's going to be separation between the two environments, right? So there's segmentation between the two, so where Bob can't get to that database directly. Accessing that CDE, in this case I talked about jump boxes, but actually there's a talk at noon about private access workstations. That's another way of getting to these secure environments. And also including multi-factor authentication. So that's a bit about what I do in PCI and the company I work for. I'm going to switch gears a little bit and talk about the employment outlook. I was expecting a lot of DSU students, prospective people trying to get into the industry. So one thing that I saw about a year ago, sorry this is so old, but this was the most recent thing that I've seen, is the employment outlook. There was a Forbes article from January 2016, and at the time, there were 209,000 unfilled cybersecurity jobs in the U.S., and that demand is expected to rise by 1.5 million by 2019 globally. Okay. Another one, I Googled like information security analyst or something like that with the Bureau of Labor Statistics. So median wage, 90 grand, and the need for cybersecurity or information security analysts will grow 18% by 2024. The moral of the story is there's a lot of opportunity in security, there's a lot of jobs, and those jobs will continue to grow. So if you're looking to break into the industry, I mean, now's the time to do it. It's exciting. A couple years in the industry, I promise you guys, you'll have lots of opportunity for growth and to move on. Let's get into what this talk is about, I guess. So when I was preparing the call for papers for this talk, I thought long and hard, like, is anyone really going to care about what you have to talk about? Yeah, I realized that I'm pretty lucky. You know, I had set a goal to become a pen tester way back in 2006. I wanted to hack. I wanted to hack networks. I wanted to hack full time. So I've been very fortunate in the fact that I get to do what I love. I have a job that I love, and the path to this point hasn't been easy. My wife and I have had to make some sacrifices to get here, but I'll explain later. I have a pretty cool job. So I've had a lot of good luck on the way, made some pretty lucky decisions, but ultimately I just want to give like DSU folks and prospective information security folks some insight about what it takes to make it, especially as a pen tester in South Dakota. You know, aside from DSU, this isn't a hot security scene, really. So let me back up a little bit here. I mentioned that I got a degree from SDSU in 2003. I didn't really have a focus. I didn't know what I wanted to do. So what I did was I got this degree in health promotion. It's just like that extra science degree that they offer here in Madison. And I never ended up using it. So I got a job working in manufacturing at a factory in Brookings. Not in manufacturing, but I was at a factory in Brookings. Going from department to department, trying to increase efficiency, ultimately trying to save the company money. I hated that job. I hated the job with a passion. I realized I needed to do something that, something else, you know. So I looked at different career paths, going, you know, with all the anatomy, the science classes, transition into an advanced degree in one of the health fields would have been easier. But I always had this nagging feeling. You know, I've always had a knack for electronics and, you know, computers and that sort of thing. And I'm sure that most of the people in this room feel that pain as well, where you're the person that family and friends go to and have problems with their computers, their phones, right? So that's what I went through. And I started looking around. I found this crazy hacking degree at Dakota State. I'm like, what's that all about? Sat down and had a talk with Josh Pauli, and he told me about the job itself, told me about the job outlook. This is like 2006, summer 2006. And at that point, I decided I wanted to be a hacker. I was like, I'm going to hack. I want to hack full time. So there was a problem, though, and that was that I was paying for a 4-5-year degree from SDSU already, right? So paying off student loans is terrible. I had no idea how I was going to pay for this degree. So I went and asked my uncle for a job, my favorite uncle, Uncle Sam, right? So I ended up joining the National Guard at 27, going to basic training. But you know, the bonus structure and all that stuff was outstanding at the time. There's a lot of money, and they paid for my schooling. So I ended up getting in with the 115th Network Support Company in Brookings, their signal unit, and they specialize in all things communications. So satellite, radio, networking, all that good stuff, they do it. I got very good training, very good experience, and I'm really glad I did it. I'm not a recruiter. I'm not trying to recruit anyone to join the Army. It's just what I did. So I'm going to fast forward a little bit now. You guys don't need to hear about my first couple years at school, sitting in the library, being boring. So let's go to my last year at DSU. This was 2009, 2010. The economy was recovering. I had no idea what I was going to do after graduation, right? I didn't know if I'd be able to get a job in security. I wanted to be a hacker. I had no idea if I would pull it off. So there were a lot of uncertainties. And again, this is just something that I did. Okay, my last year, I knew that I needed to get the right first job. Sometimes you don't get the right first job, you end up getting stuck in a career that may not be right for you. So I ended up taking out max loans, student loans, my last year, just to make sure that I could float myself until I got the right job. Other things that I did in preparation for graduation, I hit up career services and I did everything that they had to offer. Okay, so they do mock interviews, look at your resume, help you with your resume, all the job fairs. I did all that stuff, and I'm really grateful that I did. Another thing is, as you guys are getting closer to graduation and job interviews, you know, Google, if you want to be in information security, if you want to be a pen tester, Google pen tester or information security interview questions. Go off those checklists, work off of them, but also, you know, you'll discover going through those interview questions what you're lacking and the things that you need to work on professionally. So it's very useful. All right, so in the months approaching spring graduation, I had gone to every job fair. I applied for every InfoSec job within 4 or 5 states. The problem is that I didn't really have any experience. I had some Army experience, Army National Guard experience, you know, with my unit. I had what I learned in Pat's and Josh's security classes, but I didn't really have any experience. I was a new guy. And you have to realize that if you want to hack, your prospective employer really has to trust you, and you have to make an impact, like, because they're going to let you go on someone's network and do something potentially dangerous, performing a pen test. Okay, so you really do have to make a good impression during your interviews. So, like I said, I was starting to feel pretty defeated. I started applying for jobs in probably February. I graduated in May, and I didn't get a job until July. So I took out all that money, right? Fortunately, it did. It floated me until I found that right job. So what I was doing is I was focusing on jobs in 4 or 5 states. Couldn't find anything. So I asked my wife, my girlfriend then, if she would join me, if she would come with me if I started expanding my job search nationwide. And I did. I ended up getting a call from this company down in Baton Rouge, security company. Got through that first interview, you know, the one where they call you to make sure you're normal and you can speak to people. And then I'm getting a second interview, which is a technical interview, and I got through that, and they ended up, you know, offering me the job. So, well, they wanted me to fly down and meet with them, but I was too busy because there's all that flooding going on along the Missouri back then. So I was helping out doing flood duty at the Dakota Dunes. And I got that call, and I said, I'm too busy doing Army stuff. Can I just accept the job sight unseen? And I did. Ended up getting an apartment down there sight unseen. It's pretty risky moving to Baton Rouge sight unseen. But it worked out really well. I had a good recommendation on apartments, and it was a good experience. So, I mean, I did pretty well at Dakota State. I had a good GPA, worked really hard, and thought I knew quite a bit. But within my first month of starting at this job, I realized I didn't know anything. Like, I don't know anything, honestly. I absorbed as much as I could from everybody, but more of the story is learn as much as you can, and be hungry. Try to absorb as much as you can from your coworkers, from your bosses. Work outside of work to learn what you need to learn to make it in the field. So, like I said, I didn't know anything. The smartest thing I did within the first month, I signed up for the OSCP and paid for it out of my own pocket. Within my first month of work, I was getting on-the-job training. In my downtime, I was in the OSCP, working in the labs, hacking. Even during working hours, when I wasn't doing anything, sometimes I'd VPN in and hack as well. So it was one of the smartest things I ever did. So let's fast forward again. I worked for this company for a while. Like I said, I learned as much as I could, got some really great, actually. Let me talk about what I did as an information security analyst, okay? I did internal pen testing, external pen testing, web application stuff, wireless pen testing, social engineering, IT risk assessments, IT audits, and physical security. An analyst working for this company has to be able to do everything. What was great about that was that I was thrown in the deep end and introduced to all aspects of security, not just the technical stuff, but the risk and audit stuff too. So working in security, you don't have to just do the highly technical things like the blue teaming and the red teaming stuff, but if you work in the risk and audit side as well, there's a lot of opportunity there as well. Okay, so I was fortunate in the fact that I got to work for this company and do all of these cool things. So my wife and I wanted to get closer to home. This is where we grew up. We have roots here. So we ended up actually moving to Minneapolis. But the company I was working for at the time allowed me to work remotely. I moved to Minneapolis. I was working remotely, continuing to work towards my goal of becoming a pen tester, okay? A full-time pen tester. So while I was working remotely, I still continued to pen test as much as possible remotely. I traded favors for pen tests, just trying to keep my skills sharp and get better. After Minneapolis, we actually moved back to Sioux Falls, and that's where we purchased our home, and that's where we're going to stay. So all these moves down south, Minneapolis, was all to get back home, but working in security and getting some good experience, it opens up a lot of doors, is all I'm saying. It opens up a ton of doors, a ton of opportunity to eventually, hopefully, get to your original goals. So remember, I still want to be a hacker full time. The risk and audit stuff just wasn't for me, right? So social engineering as well wasn't my cup of tea. So my goal was to become a full-time hacker, and I ended up applying with this company, PSC, where I work now, and we do some pretty awesome pen tests. Okay, I work with some really super intelligent people. I've learned from some very talented people, and it's been great. So I've been doing this for a little over a year now. Let me briefly describe my work arrangement. I get to work remotely. Travel is 40 to 50%. I would say that's the only drawback. People tend to burn out after a while. So travel's 40 to 50%. It's been pretty slow for me lately. I'm required to put in 30 hours of client work every week. The other 10 hours a week I get to spend on personal research or personal development, learning stuff. When I'm working from home, I'm doing web app pen testing, external pen testing, mobile app pen testing. When I'm working on sites, I'm doing internal pen testing. So either way, I get to hack all day long. It's pretty cool. It sounds like a pretty cool job, right? So that's it. I've got this last slide here, and I kind of want to go over briefly some of the things that I view as important to make it in the industry, especially with being a new guy, being a new guy, just graduating, not really knowing anything. First thing, if you're going to DSU, be in the Cyber Corps. I wish I would have done it. You're going to get huge, lots of opportunities if you can get in. So definitely, if you have the chance, be in the Cyber Corps. The next thing is get experience. If you are flipping burgers in the summers, you're not getting the experience that you need, right? So whether it be working on internships or working on your network at home, in the summers you should be doing something technical, something towards your goal. Next thing is over-prepare for your interviews. I don't even know how many times I've interviewed in my life. I've interviewed a lot of times, and I've over-prepared for the majority of them, and even the ones that I felt that I nailed, I didn't always get the job. I thought I did really well in the interview. I walked out, I was like, that was awesome. I'll be getting a call in a week, and I didn't get him getting the job. So, over-preparing for interviews there's no harm in it. Start applying early. So like I said, I started applying for jobs in February, graduated in May, and I didn't get one until July. Of course, it was a different economy back then, but regardless, I would definitely recommend starting early. Next thing is specialize in something. If you're working on a technical job like pen testing, I don't care what it is. Just be good at something. Be able to describe something technical from the physical layer all the way to the application layer. Right? If it's wireless stuff, be able to do all the wireless attacks against all the different technologies. Be able to use different tools and be able to explain how the attack works from someone that's experienced in the industry, but also to my 3-year-old son. Right? So you have to have those communication skills to be able to break things down for different audiences. Be prepared to move. Like I said, my wife and I had to move a little bit, but it opened up a lot of opportunities for us to move back home. So we have a great arrangement now, and we're very happy. Next one, if you want to work in consulting, be prepared to travel. The last job I was at, I traveled about 20 to 25%. This one's about 50%, 40 to 50%. So if you're going to be in consulting, just be ready to travel. The last two are probably the most important things. Be humble. Everybody wants you to be the smartest person in the room. Nobody wants to hear you say that you're the smartest person in the room. Okay? I'm fortunate because I get to work with these guys that are super smart, but none of them are arrogant about their knowledge of things, right? So it's very important that you be humble in your communications with people. And also, don't be afraid to say, I don't know something. During the interview process, when you're working with people, when you're with clients, if you don't know something, own up to it and say that you don't know. Don't try to BS with them. Just tell them you don't know, and you'll figure it out and give an answer later. And the last thing is work on your communication skills. Every class that you take at DSU, they make you present, I'm sure. Is that right, Wayne? You have to do a presentation for every class. It's an important skill to be able to speak to all types of audiences, technical people to executives, but also be able to write. I've been fortunate that I can write pretty well and I can speak all right. I talk good. So I guess that's been helpful in my path to doing this. That really covers my talk. Hopefully I gave you guys some good insight into and some good advice into what it takes to make it in the field. Here's my contact information. If anyone has any questions and wants to reach out to me, certainly be happy to help you. If there are any experienced pen testers, I think we're looking for one or two. If there's anybody experienced in the room, so come get a hold of me after the talk here. I think that's it. Thank you guys.
Yeah, you're good.
Okay, test 1, 2. I think that's working, right? People can hear me? It's not just me? Higher? All right. How about now? A little better? Yeah? I'm getting a hand wave. Okay. Hand wave is good enough, I guess, as long as it doesn't feed back. Good noon. They put me right at 12, so I can't say good morning or good afternoon, so good noon to everyone. My name is Michael Edema. I'm a DSU grad. I want to talk a little bit about the Internet of Things and how they're kind of awful currently. I'm an engineer for Range Networks. We build cellular networks. We build the infrastructure, right, the software that runs on the towers, and have kind of redone the way those networks are built. But I'm not here to talk about that, so any and all opinions are my own, but I have to put a title up there, otherwise you wouldn't believe me, I guess. DSU grad. I take the little, that's my buddy, hang out in the backpack. I've been building things since 2003. This is before we actually called them the Internet of Things. That's nice and buzzwordy. They used to be called appliances or embedded devices. And I've just been kind of locked into that field since before graduation. I've built agricultural control systems, routers, wireless access points, then did an infotainment unit. Does anyone know what an infotainment unit is, or is that some horrible jargon? Yeah, it's the thing that sits in your car that plays videos and also has the radio and you control your AC, and it's info entertainment. Did one of those, business phone systems, actual desk phones, headsets, and now cellular base stations. So all of those are technically things, but they don't quite fall into the new definition of Internet of Things. So what is IoT? Appliances, devices, products. They're essentially products. They're embedded devices. It's a little computer running some software, and it's on some specialized hardware for a specific purpose. It's a very tight coupling of software and hardware. And anytime you have that, you run into some very specific issues as well. But the buzzword gods would say that's an oversimplification. IoT is much more important than just building products and selling things in boxes. It is the ubiquitous ambient intelligence that will one day surround us all, and make your life beautiful and wonderful and automatic. So when you drive your car home, your thermostat turns up and your lights turn on. And if the weight of the vegetable drawer in your refrigerator goes too low, it'll automatically reorder something from Amazon. And the closer your phone is to the door at your hotel after you check in, you automatically unlock the door. All these wonderful things. So that's all about connectivity and interoperability. All these things have to always be connected, and they have to be able to talk to each other. And they're devices, so they have to have APIs, and they have to have standards, but none of them do. So this way of building things and connecting things and having them all interact with each other is kind of inevitable. We can't just say, this is a bad idea, like commerce on the internet or banking on the internet. No one would say, well, let's see how that pans out. It's going to happen. This is what things are going to be like in the future. So Internet of Things security. This is my favorite bit of snark about that. The S in IoT stands for security. Yeah, because there is none. Right now, they don't have the best track record as far as producing devices that are reliable and secure. And those two kind of go hand in hand. If you can't even make something that's reliable and it does the thing that it's supposed to do when you ask it to do the thing it's supposed to do, it's probably not secure either. So why is that? First, how do you actually build a product? This is maybe important to understand how these things come together. You have to examine the market and figure out what people are willing to buy, what's out there. Is it junk? Is it too expensive? Try and find something in the middle there that's going to meet those needs, and you can build it at a certain price and sell it at a certain price and make money. And you also have the egos of the the leadership of your company. I've always wanted to build a whatever, and you might end up get stuck building whatever that person wants to build, even if it doesn't make any sense. You have to have access to certain talent depending on what kind of devices you're going to build. If you're building noise-canceling headphones and no one on your team knows anything about acoustics, you probably want to find someone who knows something about acoustics. And this is the end-all, be-all, most important factor in building a product. It's time to market. Doesn't matter. There's another little saying, I couldn't find the quote, and it's something like, meanwhile, while academia is studying the benefits of programming everything in Haskell and functional programming, people in Silicon Valley are shipping products made out of PHP and duct tape. It really doesn't matter. If we can get it out the door in a box and someone will pay for it, we're happy. We don't care. After it's out the door, that's when the problems actually hit. So developing the products on the software side, I'm mainly a software person. I don't do hardware. I've received the side effects of having to work with hardware, but I don't develop hardware myself. This is how you estimate software projects, usually towards management. You take your engineering estimate and you multiply it by pi, and then you give that to management. And then when you come back a little bit ahead of schedule, you're a hero, because you've done it before it was expected to be done. There's another one. I don't know if anyone's familiar with this. You do a WAG. Does anyone know what a WAG is? Yes, it's a wild-ass guess. You just say, well, that sounds like a 4-week project. I can do that in 4 weeks. So you start working on it. And hopefully after 4 weeks you have something to deliver. And if you don't, you deliver what you have. Or you lose face and re-estimate and delay your deliverable. Nothing looks good. None of those things are fun. Estimation is very hard to do correctly. You also have unit testing. You actually should write unit tests while you're building your software. That seems to be the first thing to go. If you're trying to meet a deadline, you stop writing unit tests. You can't verify that things haven't changed as you're developing your software. You also should do integration testing. Does anyone know the difference between unit testing and integration testing? I mean, just hands. You don't have to explain it. Yeah, kind of. This is the difference. If you put these drawers in and you do unit tests, each drawer works. But then when you put both drawers in, the integration test fails because you didn't do an actual integration test. That's the difference. Integration tests are harder. So they also are one of the first things on the block to get done if you have a project. You might also get halfway done, halfway through your project or your product and realize you do have to hire somebody. Some unknown reason, something changed, and you don't actually have the ability on your team to complete that part of the software. Then this is the most dreaded one. Management decides, you know what, let's not make it in a check-in app. Let's make a photo sharing app. Okay, we have the cloud infrastructure, we've got this done, we've got iOS stuff done, we've got some frameworks done, but now you just want to share pictures. Interesting. That's exactly what happened to Instagram. Instagram started out as a check-in app. They got halfway through and they went, let's just make a photo sharing app. Now that worked out well for them. So pivots sometimes work, but they can happen. You just completely change your direction halfway through. Hardware side. Feature creep is a little more disastrous on hardware. Software, you write more software. Hardware, you send it back to the manufacturer. You change your design. I had an example in the past where somebody said, this is a really cool product, but it'd be nice if the USB port in the front of this thing, we could charge our phones on it. Because, it's already on your desk. It'd be pretty cool. Well, that means they had to resend the schematics back up and have it redone so that the power routing would work for charging a phone in the front. It was just a data port. It didn't support 2 amps of an Android phone charging from it. So then you have to change your bill of materials. If you have a $99 product, your bill of materials should be $11, $12, $13. So every nickel you spend on bill of materials, that counts. If you're making a change that costs another 10 cents, that hurts. It changes your price dramatically. You have to relay out the board, you have to change your schematic, you have to get a manufacturing sample made from your contract manufacturer or your in-house development. Then somebody has to bring it up. This is to the point where it turns from a PCB sitting in a box and you can actually run software on it. So you have to get the bootloader to work, you have to get whatever really low-level bootstrappy type stuff to work and bring the thing up. This happens every time you have to spin the board or you make a change in your design. So you can go to an ODM. Does anyone know what an ODM is? Does anyone know what an OEM is? Like if you want a cheap CD burner, you buy an OEM CD burner. ODM is an original design manufacturer. You can walk into Foxconn's offices, and this is literally what they do if you want to have them build a phone for you. Then they say, well, what kind of keypad would you want? How heavy should the handset be? What does the cord look like? What color is the display? How many ports should it have on the back? And you define all that stuff. You write all the documentation, and they build it for you. It's amazing. Then there'll be like 24 coders in a room, and they'll write the firmware for your phone. But you're giving up cost, or you're giving up control for speed and cost. And you don't know really what's under the hood. If you haven't negotiated correctly, you don't have access to the underlying source code. You're just stuck with a black box. It's exactly to your definitions, but it's still black box. Okay, you got to finally ship it sometime. Finally, you decide, okay, it's good to go. And this is kind of better is the enemy of good. If you have something that's okay, get it out the door. Try it. At some point, you have to say it needs to go, because it'll never be done, because software is never done. The easiest way I've ever heard this explained is on a podcast. 2 Apple directors were discussing how they ship products and how they ship updates, and they came up with the bag of shit theorem, which is a great way to put it. You have a bag that is a certain size, and you can only put so much stuff in it. So if you know you have a year to ship a product or an update or a release, and it's a 10-pound bag, then don't try and put 12 pounds of stuff in it. The tricky thing is, though, to know how much each feature weighs. That's the tricky part. But it really comes down to that. If you know you only have so much time, don't try and put more stuff than that in there. And that's usually called the minimum viable product. And that is this little illustration. A minimum viable product is the thing that you can put out the door that people will be happy with when they get it. And it's not that. If you're trying to ship a car, don't ship a wheel. That's not the minimum viable product for a car. A skateboard is. It moves you from place to place. You're shipping a transportation product. And then you improve on it, and you add a handle, and you add a motor, and then you add a couple more wheels, and you put a roof on it. This is where I have a brief rant on Kickstarter. Who has invested in a product on Kickstarter? No, you haven't. You just gave your money to somebody. You didn't invest in anything. You invested in the stress of checking your inbox every day for the next 6 months while your money is already sitting in their account. Kickstarter's not good at minimum viable products, and they actually, by definition, don't. It seems like they don't care. Some people use Kickstarter correctly, and they do care about minimum viable product. But the stretch goals, that's the antithesis of a minimum viable product. If you say we're going to release this thing in 6 months, but if you pay us more, we'll add 7 new features, and it'll still ship in 6 months. No, it won't. It won't ship in 6 months again if those features get funded. Just because you throw money at something doesn't mean it comes out the door at the same time. It just doesn't work. MVP. Okay, so you got it. You're happy. Management's happy. You're all signed off. Now, do you ship it? You're ready. That's it, right? No. You have to make it. Now it's ready. Now you actually have to make it. This I've heard before. It's the 90-90 principle. It's like my favorite part of any project is the first 90%, and my second favorite part is the last 90% of a project. It's these last 10% of actually getting it out the door that turns into a nightmare. So you've made a few things. You have your team. You have a dozen programmers, a dozen hardware people. They all have copies of the thing. They have examples, but they're all one-offs. You've resoldered wires that have broken because they're all prototypes. You have a breadboard on top maybe. You all have like desk mounted or desk power supplies. Nobody has the actual power supply. Nobody has a case, just a plastic case. Maybe you have a 3D printer. So you make like 10 of them in the actual production process, and then the regulators actually have to approve it. And that might change your design too. Hopefully you've been paying attention to this the whole time, but if you have some interference problem, you have to now fix it for the regulators. When you finally get that locked in, then you do tooling. This is tens of thousands of dollars to set up the manufacturing equipment to stamp out these things in mass. You have to set up the tooling for the manufacturing process. You don't do that until you know you're 100% good. If you have a problem on the other side of tooling, you might as well just get fired. Just quit. You have made a big mistake. So you make 50 of them, and you do some manual quality assurance. And then somebody sits down and writes a test harness to automate the quality assurance and test suite. The test harness is actually usually another piece of hardware that you have to build. Like you build a gigantic lunchbox that you put these things in, you hook up the cables, somebody hits a big big button, and a light either goes green or red to say that this thing passes. It has to be that simple. Then you make 500 of them and really hope it's still, your QA is at the percentage of pass-fail that you want. And then you start making 500 of them a week. Now you're really in deep. If you have a problem here, then you've recalled, well, then you're Samsung with an exploding battery. No. Oops. Small mistake. Contract manufacturer, you might do that. But they have to be told everything. They have no self-drive other than they cash your checks and they build your things, but you have to tell them exactly how you want your things built. You give them everything. You give them your schematics, your bill of materials, your design. They own it 100%. We've actually had instances of this in the past where somebody had sold our contract manufacturer's design to another contract manufacturer in an inside job. They were building 100% perfect copies of our product and injecting them into the sales pipeline. But we had no idea. And they were taking all the sales for that. They were just building our product on the side, putting it in similar boxes and injecting it into the distribution chain. So they literally can make a 100% copy of your product, even at that point. Awful. Launch, you're ready. It's really, we're finally there. This was an intro, but we're finally there. We just have small stuff like all of the documentation, the box art, somebody has to actually Photoshop this thing together and make it look amazing, and the marketing materials. Then you get your website ready and you launch it. And it's out the door, and then you go on vacation because you've been through a nightmare for a year, maybe. And the last 2 months of that year are just weekends and nights and constant work to try and get this thing out by the day that you said you were going to get it out. So did you forget anything in this whole nightmarish process with all these moving parts and teams and everything? Maybe the security. It doesn't show up anywhere. It has to be part of the product from like the very beginning. You have to be thinking about it from the time you start designing it to what interfaces are going to be on it, the physical hardware of it. It takes time, it takes effort. Somebody has to be paying attention to it. You also have to test it, and it changes the entire design. So, and of course, it only takes one little vulnerability, and all of your lovely planning has been ruined. So that's it. I could stop the presentation right here. That's why most of the Internet of Things products suck, because nobody sat and thought about the security from day one. So why are they maybe, not why are they insecure, we know why they're insecure, but why does it keep kind of happening, and why does it make so many headlines when it does happen? Well, they're things. It's not a web app that gets exploited and, if you put in this certain URL, you can open the back-end database and look at a bit of secret information that you weren't supposed to. They control and monitor physical objects, like your window shades and your thermostat and cameras, kitchen appliances, outlets, lights, cars, small things like cars, locks, and they're more fun to attack. If you can open someone's window shade or turn the heat up in their house, it's kind of, check it out. And then you have access to their camera and you can see them running around, or you can voice over through the camera, like through a baby monitor, and like, hey, I'm in your kitchen, and then you turn on their oven. It's fun. Of course, that's going to be the thing to attack. But they're also headless devices. So if you're hearing a voice come out of the baby monitor, and it's obviously not your child because the vocabulary is slightly different than what they would be using, and your oven turns on, what do? You just shut off the router or something, you unplug everything. But you don't have any other options. You have an app on your phone, and it's lighting green, like, all good, we're all connected, and a couple of buttons on your devices. That's it. They're designed to be very simple and easy to use. So there's no feedback. There's no, yellow light that comes on that says something's a little strange. There's no way to debug it, and then you're just stuck with it. You only have APIs usually to deal with these things too. They're completely locked down and you have some APIs. But underneath all that, it's usually still Linux. So if you do know what you're doing and you get access to Linux underneath it, you can still perform all your familiar attacks and exploits because you have access to a full Linux box. And these things are very powerful too. They're getting to the point where, well, when I was a kid, the desktops were about as fast as some of these little system on chips. So they're always on and always connected. They have to be. If they're not connected, they're not smart devices. Smart devices are connected. Dumb devices aren't connected. It's also a great place to camp inside the network. Once you get inside there, you can just sit on the underlying user space of some Linux system that runs a baby monitor, or runs your oven or your microwave, and just sit there and execute other attacks. It's a nice little home base. Because reachability in these things is actually a feature. That's what they're supposed to do. If you have a new smart bulb at home, it connects through your home network and goes out to the cloud. Hey, the cloud. Everything's in the cloud. But here's a small secret. It's just somebody else's computer. It's not the cloud. It's not some magic infrastructure that is impossible to hack into. It's just another set of servers. But you just don't have to worry about it. So why does everything connect out to the cloud? Because home routers are awful, and the only way to reach something like that is to tunnel out. It's reachable by the cloud, and then you ping it via the cloud. It tunnels back into your network and talks to your light bulb. So if you're talking about a light bulb, that's pretty cool. But what if the cloud doesn't work, and you're sitting at home on your couch 6 feet away from your light bulb, and you can't shut it off? I mean, that's a little sad. So a little sadder cloud. It's not quite as wonderful as we all think it is. But everyone's running their own clouds, right? Everyone has their own infrastructure, right? Or maybe not. They don't quite all have their own infrastructure. They all kind of use the same infrastructure. So when AWS goes down, Amazon Web Services, if that goes down, all your stuff doesn't work. All your products are dumb. They stop working. S3 too. You just got to name both of them. So, not the happiest cloud. And if your phone can reach it, then anyone with a computer can reach it too, because it's on the cloud. It's on the public internet. So it's really pretty sad cloud. Now you're really exposed. But people aren't that bad. Not everyone's out to get your home network, because who cares? It's just your couple of devices that you have inside your house. Well, what if it was like a virus or something, and it really attacks the cloud and doesn't care if it's your bulb or your house? It just cares that there's a bunch of these little tiny embedded devices floating all over the internet, and they're all connected to each other, and they're all online all the time. What could you do with something like that? Well, let's get an example of what kind of devices these are. I've talked about light bulbs and some other things. So what if it was a lock? There's smart locks now. Then you get stuff like this. So I have a 3,000 euro bike, and I can't unlock it because the cloud's down. I have an app on my phone. I try and unlock my bike. It doesn't work. So your bike is stuck locked. Or maybe your dehumidifier doesn't connect out to the internet correctly. It doesn't know when to shut off. And so it just keeps dehumidifying and spilling water all over your living room. What if something could explode? That'd be kind of bad. But they wouldn't make an internet-connected bomb unless it was like a pressure cooker that you access over Wi-Fi. Slow cooker, pressure cooker. I like this. It might be a little small to see, so I'll read it. If there's one minor con, it would be that if a phone call comes in while the pot is running, or something else comes along that interrupts the app in the foreground, Bluetooth connection is lost and cannot be reestablished until the pot stops cooking. Well, that's a good design. That's nice. Maybe a fire. Here's an internet-connected oven that's supposed to let you control your oven via a smart app so that you can feel rest assured that when you're out of your house, you can just check, did I shut off the oven? Oh, I did. Look, it's off. And if it's not off, you can turn it off. So that means it can actuate the gas in your oven via the internet, via a publicly accessible service. Brilliant. What's that? No big deal. Just a toy doll that's publicly accessible, and it can spy on your kids because it's got a microphone and a speaker in it. They were actually hacked, and the database was exposed. They held all the voice recordings and interactions with the parents and the kids and the doll ransom until someone unlocked the database and paid the ransom. So not a good start for the IoT. What makes them so easy to attack? They have a very predictable attack surface. If you're talking about a desktop, well, you have Linux, million choices there. Windows, fewer choices. And then Mac. But then on those operating systems, you have different packages that are installed, different services that are running or inactive, firewalls, secondary devices on the other side of them, whatever. With a thing, all you need is the product and the version, and you know exactly what the environment is inside that device. You know what user space things are running, you know what patches have been applied or not, which libraries it was compiled against, you know what version of OpenSSL is in place. And since most of them run out of a RAM disk, you can just try things. And if they don't work, you restart the device, and your environment's exactly back to where it was. Does anyone know how a RAM disk works? So if you have a little embedded device, you don't have a whole file system and a hard drive in it. You have one file that contains all of the operating system and all of the underlying files and programs and executables and everything. It's all compressed into one file. And then when the thing boots up, it expands that file into RAM. So you can do whatever you want to the device. So I have a quick demo. Hopefully I can do the screen magic to get this to work. Let me see here. This is a product that I work on. This is a cellular base station. Well, that is quite small. That's not good. Let me see here. You can just do that? Nope. I'm sorry. I didn't really plan this out. Well, I will tell you what I'm doing, and I hope you believe me. So there's super secret option 8 that drops you into a shell. Everyone knows that. It's not a secret I just revealed about the company. So I have a full shell on this embedded cellular base station. It's a 3G base station. Could be up on a tower somewhere. And, well, I want to try some stuff. So let me see what's in here. I can list, etc., see what's in that directory. I can touch a new file in that directory, just add a new file and etc., test. Okay, that doesn't do what I want it to do. I can remove some stuff, or I can do remove rf/. Right? Does anyone know what that does? If you're on the Linux command and you do rm/rf/, it removes everything in the file system. Just mercilessly tries to delete every single file in the file system. So I'll run it. And it's going to complain about different things being mounted read-only and the proc file system not wanting to be deleted itself. And it's basically making the thing very, very, very angry right now. And if I go over to where it's open, sorry, here. Oh, this is the interface for it. I bet if I try and reload this page, it doesn't work very well. Yeah, no, the page is gone. So it's dead. I wonder if I can even get out of here. Well, it can. What if I try and exit out here? Yeah, it can't display the terminal banner because that's gone too. That's not good. If I try and reboot the system, let me see here, 5. It can't find the reboot logic. That's gone. That's not good. So my experiment didn't work, right? I'm trying to exploit this system. My experiment didn't really work. RM, RF, not a good task. I'll just shut it off. Just power the whole thing off. And I'll turn it back on. Well, there we go. It loads the one file that everything's compressed into, expands it into memory, and all the scripts are back, and it boots right back up. Because there is no actual file system. It's just stuck in RAM somewhere. So that's basically the core problem, is you have this perfect environment that you can test with. You can test against. And then it's really easy to propagate exploits, because who's done this? Default password for because I can't find the documentation for my router, so I'll just type it in. It's right there online, and most people don't change their passwords. So it's pretty easy to compile a list of default passwords and usernames like this one that's in a little piece of software called Mirai. Has anyone heard of that? That was pretty popular last year or the last few months. It's a bit of malware focused on Internet of Things devices. The source code also is completely publicly available, not just for the exploit itself, but for the command and control server. So if you want to make your own little private Mirai-based botnet, pretty easy to get started. You have your development kit. It's right there on GitHub. So what do these things do? If you have an infected device, it's going to continue to function normally, except for occasional sluggishness and an increased use of bandwidth. Well, you're not really going to notice that if it's a camera or an audio device or it controls your oven. You won't notice that it took an extra 100 milliseconds to turn up the gas actuator on your oven. So you have no idea that this thing is there. It remains infected until it is rebooted, which may involve simply turning it off. After a reboot, unless the login password is changed immediately, the device will be reinfected within minutes, because there's probably another device on your network that's infected, and they just keep cross-infecting each other because they can. Hundreds of thousands of these things have been infected at the last news article. And yeah, many derivative botnets already in the wild. You can change a couple of keys and command and control server addresses, and you have your own little botnet. What have they done with this? Small DDoS at 620 gigabits a second on these are little tiny devices all ganging up all over the internet. Another one, terabit a second. That's officially big, I think. That's a large attack. A lot of bandwidth there. Because all these little SoCs, these little system on chips, they have 100 megabit connections. They're not slower than your desktop. They have 100 megabit. They might not have a gigabit connection, but they have 100 megabit connections. So they can max out most anybody's residential internet connection. Another small attack against DNS, GitHub, Twitter, Netflix, Reddit, Airbnb. Yeah, that's basically all comes down to this. Doesn't take a lot of computing power to drive 100 megabits of traffic now. So why don't we just update everything? Just keep updating all the devices. Well, updates are tough. Even our phones. iOS is a direct update from Apple. They have complete control over the update chain. Your phone says, I'm not on the newest version. You go, and it updates to the newest version. Android's not the same, because you have provider, carrier, junk injected onto Android. So then it's up to the carrier to say, yes, we want to push this update out to you. So there's a huge delay there. That's what happens if they're too seldom. If they're too often, your devices are down. They're not doing what they're supposed to be doing. So there's some sort of happy medium in between those two things. If it's interactive, people tend not to do it. If it's autonomous and it doesn't work, then you start to gather a reputation as a product saying, well, it updated itself and it doesn't work anymore, so this thing's a piece of junk. Chrome does a pretty good job. Have you ever updated Chrome? Has anyone updated Chrome? No, because it does it in the background. It might prompt you, like it's been open for too many days, you should probably restart it because it's out of date. But that's it. They have update channels. Some are updated more frequently, some are updated less frequently. The dark side of all this, updates aren't possible if there's no money. So if your product's not successful, it's not going to get any updates. So you might have 1,000 of them in the wild, you might have 10,000 of them in the wild. If you're not making any money, they're not going to get updates ever. They just stop. And eventually someone can't pay the cloud services bill either because your business model is garbage or your product is a piece of junk. But there's a lot of people who already have the product and they do kind of like it, even if it's not the greatest. So your cloud disappears too, and then you have a thing that doesn't have a cloud, which means you have a doorstop. It is worth nothing. This is the biggest one. What would happen if you had one of these devices and you've done everything right? Everything's right. It's updated all the time. You have a great product. It's used all over the world. Billions of devices already out in the wild. But something about the protocol is inherently flawed. That would be bad. Most commonly you see this with TLS. They don't put the full certificate chain on the device, so they can't verify upstream certificates. So they just have some encryption in place, but there's no certification verification possible, or they kind of eliminate the full spectrum of TLS options to save space. So TLS is usually kind of junk on these things. But yeah, what if one was like intrinsically flawed? The protocol itself is garbage, and there was no way to update everything. Like, what if there was this thing that was in point-of-sale machines and like parking meters and industrial sensors and command and control structures, and it was really literally everywhere all over the world, and it's been there for like 10 years. That'd be horrible if something like that was actually out there and you couldn't update it. Well, that's GSM. The GSM protocol is GSM standards. They're flawed. There's no way to verify the network. So it's always possible to do a man-in-the-middle attack. GSM devices are susceptible to man-in-the-middle, and they always will be, because there's no way to update the standard. They're already deployed. They're stuck in baseband code that you can't change. But now we have two-factor authentication. That's great. That saves us, right? Until they discovered that SS7 is also equally exploitable. SS7 is the core network that connects all the mobile phones in the world. SS7 is exploitable. You can intercept two-factor authentication tokens, inject your own, whatever. So, not so good. Hopefully they don't make that mistake again. There's been some new research that kind of shows this may be happening with other protocols. They may be intrinsically flawed, and then there's nothing you can do. So this sounds like a bleak future. At least there's only going to be 50 billion devices by 2020, so, you know, should self-regulate. Then they updated that estimate after a couple years and said, well, it's only 30 billion. So, you know, let's not go crazy. And somebody else said it's 28, guys. It's actually 28. Okay. Estimate 2016, there was 6.5 billion devices out there, and they count them in different ways. Sometimes they're just actual IoT devices. Sometimes it's connected devices, which is this thing and my phone and, you know, the projector maybe. So there's different ways to count them. Whatever happens to be the case, the market is going to self-select. If you build junk that is not reliable and is not secure, people won't buy it after a while. So it is kind of self-reinforcing there. There's going to be new approaches to security. There's a company called Pipe. They've invented a way of authenticating Internet of Things devices against each other in a decentralized manner. Like just between the devices, they build a chain of trust within your house. And that is a really unique approach. So we'll see if that pans out. They have a development kit, and it's pretty cool stuff. So more things like that are going to happen, where you have different technologies in play other than the standard server-client model, which might not work for IoT. And that's going to lead to some sort of commoditized product base. You want to ship a product that's an IoT device, buy this base starter kit, plug in your 3 things on top of it, add your value, and send it out the door. And we'll take care of the security and the updates and all that stuff. So that's going to happen too. Right now, it's kind of just buyer beware. Get your reviews. Don't buy things when they're fresh off the shelf. Take a look, see if they're really going to do what they say they're supposed to do. But our Jetsons future is inevitable. It's going to happen. It might be a little bumpy, but we're going to have all this cool stuff. And it should make everyone's life easier. The smartphone certainly did, except everyone just stares at it now, so I don't know. Anyway, it's going to happen. Hopefully we figure all this stuff out. That's, I think, what your job is as graduates. So this is what you have to go up against. Questions? Anybody? Please. Or cell phone stuff. I normally do cell phone stuff. So.
Did you say the company Pipe or something they designed for IoT authentication? That's the name of the company?
Yeah, the company is called Pipe. It's pi.pe. Yeah, pi.pe, like pipe. And they have a development kit that uses decentralized authentication. It's a very unique approach. They're patenting around it right now, and it's interesting because it's completely different. They've kind of figured out that the client-server model that's been around since the 60s or whatever might not work. It just might not work at all. It doesn't scale to that level. So they're figuring out a different way to build authentication and trust chains within a product set or within your house or your business. If not, no big deal. I'm not going to stand and stare awkwardly. Anyone can pull me aside. I'm here all day. And if you have GSM questions or base station questions or IoT stuff, product stuff, whatever, bug me. I like talking. So, all right. Oh, hey.
I have a question. So the hacks that they're using to hack into the cars through your cell phone, is that possible?
Yeah, car hacks. Car hacks are possible because of something called CAN. It's a standardized way of addressing things inside your car. All cars have a standardized way of having their components talk to each other. So if you're a manufacturer of air conditioning control system, and I'm Pioneer and I make head units for cars, they both speak CAN. It's a bus protocol. And since everything speaks CAN, if you get a CAN decoder, some sort of CAN entity into that network, you can do anything. You can steer the car, you can press the brakes, you can turn up the radio, you can turn on the windshield wipers, anything. It's all CAN. So if there is a security hole from the public internet, like they had with the Jeeps, Jeep had a great exploit last year. They had a way to tunnel CAN traffic into cars. So they could exploit the car and then tunnel CAN traffic into the car that says, press your brakes, or never shift out of second gear, or whatever, and the car would do it. Very bad.
On that point, there were people that said that they cheated because they took a Jeep and they hooked computers to it and figured out how the code worked. Well, what are the bad guys going to do?
Yeah.
They're gonna take
Oh,
it
yeah,
out,
exactly.
They're going to figure it out. And
Yeah, they accuse that group of, creating a unrealistic lab environment, essentially, for that exploit. But then they were able to demonstrate later that they could replicate it on a untouched Jeep, on a Jeep that they did know the VIN to. So you'd have to know the VIN number of the Jeep. But after you knew that, you could exploit it without any further intervention, nothing attached inside the vehicle.
you can get the VIN by walking by.
Yeah, sure. It's right in the front left corner of the car, always. You can always see it from the outside. Anyone driving a Jeep? Oh. All right. Okay, thank you.
I've been doing presentations on IoT. And
Oh, okay.
Just from a different point of view, just the technology, problem solving,
Sure.
possible solutions, and stuff like that. I really like the point about why there's a problem. And in mine, I talk about in any type of device, whether it's a computer or whatever, that security has to be involved from when you're looking at the requirements.
Yeah.
And I work with organizations, and they'll bring me a final product and say, okay, test it and make sure it's secure. You should have told me back when you were at the very
We're
beginning.
building it, yeah.
And of course, it's not secure. And I don't know what this. Well, one is possibly smart homes.
Yeah.
But then you would have to at least be closer. And the fact that it's using not just wireless but also
Good. Some people are, some people aren't. Usually get the group that clips it like over here and then talks
Yeah.
this way.
Right.
Yeah. So, I think anytime you're ready to go.
All right. Hello, everybody. So, due to some flight booking failure, I managed to arrive exactly on time, as opposed to with time to do literally anything but get here. But let's go ahead and begin. This is the Practical Crypto Boot Camp for the Math Phobic. So I'm going to go through a series of agenda points covering major areas of practical crypto attacks that you can understand and then do. So you might be thinking, well, no, probably not. But wait, don't be scared. Maybe you're scared. I'll see you scared. Don't be scared. Because crypto seems really hard, but actually it's this hard a lot of the time in terms of practical attacks. Now, if you're talking about attacking, some particular algorithm, okay, yeah, you're going to need some math. If you're talking about proving the security of a particular algorithm, you're going to need some math. But actually, attacking crypto systems in practice can be very, very easy because a lot of people get it wrong. And there are tools available. Now, I want to talk about a thing called malleability. Now, malleability is the property of a crypto system or some piece of encrypted data or ciphertext, as I'll call it throughout this, just because that's easier. Plain text, by the way, is the unencrypted form of data. And a quick PSA. Encryption is not the same as signing. A lot of people make this mistake. This is like huge. If you just pay attention to what's happening for the rest of this talk and think about this point, that encryption is different from signing, you realize that you can stop about half of these attacks or more. So encryption protects confidentiality of data. Signing protects integrity of data. And in a lot of cases, we'll see that attacks on integrity can lead to attacks on confidentiality. Take, for instance, what if you could make targeted changes to a piece of data that you know that at a certain place it says to Bob, and you could just change it in some way to make it say to Eve, right? All of a sudden, if we're talking about some IM, some email, something like that, all of a sudden this is a break on confidentiality. And there are some more interesting ones that we'll talk about, but let's go ahead and move on. And sometimes I get ahead of myself and talk about what's on the next slide before I actually get there. So the one thing I didn't cover here is that there are authenticated encryption modes like GCM or EAX, and we'll talk about cipher modes a little bit later, which actually do both for you. They will protect the data from being tampered without it being noticeable, and they will also protect from an adversary being able to read the data without the key. One thing that I want to talk about before we get into anything else, this is about the closest we're going to get to like math per se. This is Boolean logic. I don't think of this as math exactly, but this is the same sort of thing that goes into your processor. XOR gates. I think XOR gates are actually Turing complete, that you can build every instruction needed to make a modern processor with just XOR. So it's a really, really cool operator. But basically the way it works is either but not both, right? One or the other. Another way that you can think of it is when you take a bit, a 1 or a 0, and XOR with a 1, it changes the value of that bit. And if you XOR it with a 0, it doesn't change the value of this bit. And this is something, it's helpful to think of it in this way for some of the attacks we'll be talking about. And the other thing that I want to say, which I've kind of expressed in sort of pseudo-assembly, is that anytime you XOR something with itself, you get 0. And it stands to reason because you'll only have XOR 0 with 0, so the 0 doesn't change, and you'll only have XOR 1 with 1, so the 1 changes to 0. So anything XORed with itself is 0. And this is actually used in a lot of exploits. If you've read Smashing the Stack for Fun and Profit, the way that Aleph1 deals with having a null byte embedded in the shell code, which would normally terminate a string, he changes move EAX 0 to XOR EAX EAX.
So you load 0 into the EAX register, but you do it in this tricky XOR way. If you have any 3 values, or actually a whole bunch of values, XORed together equals some other value, you can exchange any of those values around. You can switch them into any order, even change which is on which side of the equal sign, and it still actually holds true. So, good to remember. Now, let's get on to an algorithm called the one-time pad. Has anyone heard of the one-time pad before? Okay, a couple people. So what you've probably heard about it is that it is mathematically proven to be impossible to attack. Kinda true. So it is mathematically proven to be impossible to attack. Asterisk, 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 asterisk. There's a bunch of caveats there. Caveat 1 is that this is against an adversary who only has the ciphertext. No other advantages, and that's not usually a realistic model. We can usually at least get something encrypted on our behalf. We can usually get something decrypted on our behalf, or some small information leak. But that said, we can also tamper with this. Like I said, encryption versus signing, you can actually just flip the bits in the ciphertext, and that will change the bit in the plaintext once that XOR operation is reversed, right? So if we take to Bob and encrypt it under this given key. Oh, I forgot to even explain what the one-time pad is. So basically, the one-time pad, you generate a whole bunch of random data exactly as long as the message you want to encrypt, XOR the two together, and that's your ciphertext. You XOR it with the random data again, and that's your plaintext. So as long as you have a trusted channel by which you can transfer all this key material, and the attacker only gets the ciphertext, and for some reason they can't modify it, and you've generated the data in a completely random way, then the one-time pad is provably secure. So that's a lot of caveats, and this is why the one-time pad fails in practice. And most of this comes down to key management, because if you can send a message that's, let's say, 100 bytes long, but first you need to find a secure channel that you trust that will allow you to send 100 bytes of data so that you can send 100 bytes of data securely, why not just use that trusted channel, right? So in practice, this is not really practical. And here's the attack that I was talking about. So you take the difference in bits between Bob and Eve and apply those bit flips, those edits, to the ciphertext. And then once you decrypt it with the same key, it comes out to Eve instead of Bob. So if you know what the plaintext is, you can change it to be whatever you want it to be with the one-time pad. Now, the one-time pad isn't used much in practice, but you know what is? Stream ciphers. Has anyone heard of RC4? RC4 is a stream cipher. So basically, with a stream cipher, people were like, okay, one-time pad has this really cool property where it's provably secure against ciphertext-only attacks. That's great. That's awesome. But this whole key generation business, this sucks. So let's make a pseudo-random number generator that we can use that's, for our purposes, effectively random. Because we don't care if it's actually random, and we can talk all day about how things may or may not be random. But let's not even touch that just yet. So a pseudo-random number generator will generate for a given starting value or seed the same random-looking data. Under statistical analysis, it will look random. For all intents and purposes, for what we're actually needing to use it for, it's random. It's unpredictable unless you have that seed. So this is great because now we can just exchange a small value and attach a counter to it, use that as the seed, and then we can generate huge volumes of unpredictable data and use that with the one-time pad algorithm to achieve really strong security, except against attacks on integrity. So this is vulnerable to the exact same attack that we saw on the one-time pad. flip a bit in the ciphertext, it flips the same bit in the plain text. So encrypt admin equals 0 with RC4, give it to a user as a cookie, and say, hey, here's your authentication cookie. This is your user privileges cookie, rather. You flip the last bit in that cookie, and all of a sudden you're an admin, right? So again, please sign your ciphertexts. Okay, so I want to go over this just very briefly because it's an example of how you might go about building a cryptographically strong pseudorandom number generator. The properties are such that you can't take some chunk of it, even if you know all of the plain text but one bit. You should not be able to perform some operation on it like an XOR and then apply that somewhere else. And that's another thing you can do with a one-time pad, by the way. If you send a message twice, if you send 2 messages under the same pad, the same random data, you can XOR the plain text and the ciphertext together and get the key, the random data, because the random data is effectively the key. Then you can take that data and XOR it with your other message, which is basically the same as the decryption operation, and you have now got the plain text for this message that you didn't know. So that's fun. Anyway, we don't want to be able to do that. So here's a way that you might be able to build a CSPRNG with SHA-1. So you take some static value that you agree upon in advance, like foo. Probably you want to choose something stronger than that, but just for sake of example. And then you add, foo123, where the random value is that 123 is going to be different for every message you send. Now, if your message is longer than the length of a SHA-1 hash, what you're going to need to do is create multiple ones. But you don't want to hash with the same value over and over and over again, because then you can use statistics to say, okay, well, the hash is most likely this, because when I use these values, it comes out to the right character frequency. But if we just add a different number, a counter, to each hash that we have to generate to reach our required key length, then we can't really make those, unless we have all of the material that goes into this, or we can brute force the material, which is obviously a concern. This is reasonably secure. Now, this is just a toy. This probably has problems. I'm a cryptographer. I'm not your cryptographer. Please don't use this in practice. Anyway, as it turns out, Java tried this, and it didn't quite work out because SHA-1 doesn't produce exactly evenly distributed hashes, so you could do some statistical attacks there. But this is just, like I said, a toy. Key reuse. We already talked about this. So again, I got ahead of myself, talked about stuff on slides I hadn't gotten to yet. So now let's talk about the other main class of modern ciphers. So we talked about stream ciphers. Now let's talk about block ciphers. I kind of get the feeling I know what the answer to this is going to be, but how many people have heard of AES? Okay, yeah, I figured most of you probably would have heard of AES. So AES is the most popular block cipher. So basically the idea behind block ciphers is you start with this, again, like stream ciphers, this really, really strong, provably strong concept. And then you kind of water it down to make it actually practical enough for real use. So on one side, you have all possible plain texts. And by the way, block ciphers can only encrypt a particular amount of data. So in the case of AES, for instance, you can only encrypt 16 bytes. No more, no less. That's how AES is built. Now, you might be saying, no, you're wrong about that. I've used AES on less or more. We'll get to that. But for now, just trust me. AES only works on exactly 16 bytes. So on the left here, we have all possible 16-byte messages unencrypted, and on the right we have all possible encrypted messages. So every possible 16-byte value on the left, every possible 16-byte value on the right. Now, what we do is we make a purely random mapping. We, build a wall of lava lamps and take a picture and then use the image data combined with some like radioactive decay and then, I don't know, whatever else, some really good source of randomness to generate a mapping between all of these. But there's a problem here of practicality. There's a lot of possible 16-byte values. There's a lot of them. So in practice, this doesn't work. We don't do this. So instead, we'd make a pseudo-random mapping. Because if we were to store under this scheme, for one key, the number of gigabytes that you would need is a 301-digit number. So a lot of space, probably more than the entire world has put together. So instead, we have a mapping from plain text to ciphertext that's pseudo-random, right? We do something that without the right key, you can't really predict, right? So, and that mapping must be permuted by a key because that makes it a stronger scheme, right? Because if you couldn't do that, then as soon as somebody knows the algorithm, it's broken. So, like I said, you might have said to yourself, AES can take more and it can take less than 16 bytes. So if you're telling me that AES is a function that can only take and return 16 bytes of data, how does it work? Well, if you have more than 16 bytes, you need to operate AES outside of just its primitive form. You need to put it in some sort of mode of operation, a block cipher mode. And if you have less than 16 bytes, you need to pad out to a full block. So the simplest block cipher mode is called ECB. Has anyone heard of ECB? Right. And you've probably heard that it's terrible. Well, let's talk a little bit about ECB and why it's terrible. So never use ECB. If you take nothing else away from this, just never ever use ECB. Unfortunately, it is the default cipher mode in a lot of libraries, which, another conversation for another time. But so ECB, basically you just take the data, split it up into chunks that can fit into the block cipher, process them each individually, and then glue them back together. That's ECB. It's very easy to understand. It's a very naive construction, but there are problems with this. Has anyone seen the ECB penguin before? So you might have seen this and not known what this is about. So basically, you probably don't see anything here because this is an image whose data has been encrypted. And because of the fact that it's been encrypted, you shouldn't be able to see anything because it should be all scrambled. And so clearly nobody in this room can see anything in this image, except you can because it's Tux the penguin. And this nicely illustrates, pun totally intended, the problem with ECB, which is that patterns are revealed. So you can see that every time a particular 16-byte value goes into AES, the same 16-byte value comes out the other end, because AES is deterministic. For the same key, you're going to get the same output for a full block of zeros, which is the color data for the white background. So the white background is very easy to see there. Now, you can see that other patterns are revealed as well. The black of Tux's skin, Tux's feet can be seen pretty clearly, but around the edges it's a little weird, a little noisy, right? So there's worse problems with ECB though. This is not the worst problem with ECB. So bit flipping is something that works really well against stream ciphers, right? We have a lot of control. Stream ciphers are very malleable when it comes to bit flipping. On the bitwise level, stream ciphers are easy to control. With ECB, bitwise, it's kind of hard to control. But blockwise, it's more interesting. So you flip one bit in one of the encrypted blocks, and once you decrypt it, what's shown in red is not the actual value after encryption, because that would be ludicrous. But instead, the value after decrypting again, right? So just keep that in mind. And this is not the actual value. I just made this up, but you get the point. One block is corrupted because a small change, like you might see with a small change to the input to SHA-1 or some other hash function, results in completely different results. Now, if you take the encrypted version of Yellow Submarine under ECB, and then you cut off the second block, now you have the ciphertext for Yellow S, which is interesting, and we will talk about this a little bit more in a moment. You can also construct the ciphertext for Submarine. And this is this whole block reordering, duplication, truncation, removal is called ECB block shuffling. has various names, but that's the one that I like best. So damn it, that's the one I'm going to use. So the way that we address these is by adding a little bit of permutation, right, in a mode that we call CBC, or chained block cipher mode. Now, the way that this works is we have our same, split up and individually encrypt or decrypt. This is CBC in decryption mode. But after we're done decrypting and in encryption mode, before we even put it into the block cipher, we XOR that block with some value. Now, for the first block, we just make up a value. We just choose a random value, and we XOR that. For every other block, we use the ciphertext as sort of the initialization vector, right? And so we chain the encryption to make it look different every time we encrypt the same block. So assuming that you choose random initialization vectors, every time you encrypt the same value, it will come out to the same length because it has to fit in a certain number of blocks, but it will look different every time, even though it decrypts to the same value, which is pretty cool. Now, what happens if we change a bit in the initialization vector? Well, it's pretty cool what happens. We get our ciphertext decrypted through the block cipher, and then as the last step in decryption is an XOR step, kind of like we have with stream ciphers, we can do a similar attack on the first block. If you can flip bits in the initialization vector, the corresponding bits in the first block will be flipped. So you can do similar attacks on integrity with CBC mode if you don't sign your ciphertext. Now, what happens if you flip a bit in one of the blocks of ciphertext? Well, you've changed what's going into the block cipher, so you're going to get a drastically different output, and you're basically going to get a pseudo-randomized output. You're going to get a completely different result for the first block. However, that ciphertext is being used much like the initialization vector was for block 1, and so you can flip arbitrary bits in a block so long as you are willing to sacrifice the value of the previous block. Now, you might think to yourself, how practical is this? Well, this is a really, really practical attack, in fact. This was used to both break BitLocker and LUKS, two full disk encryption systems, one for Windows, which you're probably more familiar with, and one for Linux. And the reason that this was able to work was because when you fully encrypt a disk for some given version of some given distribution of Linux, let's say, the same stuff is going to go in the same place as far as what you install, like when you install the OS, right? And so those OS components are always going to end up in the same place. So as long as you know exactly what operating system you're dealing with, you can install that and then change some piece of code somewhere to basically give you a shell, right? You just insert some shell code in the middle of something that was doing something else, and then all of a sudden it gives you a shell, and now it doesn't matter that your disk is encrypted. I now have control of your machine, and I can read whatever I want on there. So that's pretty cool. So Burp Suite has some tools to work with this. The intruder tool out of Burp Suite has both a bit flipper and an ECB block shuffler attack mode. Bit flipper is really useful to figure out exactly what you're working with. There's the ECB block shuffler, which does exactly what it says on the tin. And then there's also an extension that you can get in the BAP store, or probably download and install manually, called Crypto Attacker. And this does a couple of things: padding oracle attacks, an attack on ECB that we don't cover here, but it can do some cool things. Oh, by the way, Feather Duster and Cryptanalib, you'll see those come up a lot. Those are tools that I wrote to make it easier to break encrypted data. So you just feed it encrypted data, it tells you as much as it can about it, and suggests attacks that you might try to launch against the system where you got those from. So I'll mention that when it's relevant. Oracles. So we talked a little bit about the one-time pad, and I said that under ciphertext only attacks, that is, where an attacker gets the encrypted data and doesn't have any other advantages, they can't do anything, right? And then you have the attacker who can, tamper, right? You have like a man-in-the-middle type attacker. A more powerful attack is when you have what's known as an oracle. Now, an oracle is basically a system that takes some input from you and performs some crypto operation and then gives you some data about that operation, whether it's something that happened in that operation or something that happened as a result of that operation, or it might directly give you the result, right? Now, again, got ahead of myself. So encryption oracles, you give it data, it encrypts it and gives it back to you under some key that it will not reveal to you and that you don't know. Decryption oracle, same thing in reverse. Format oracle, you give something data, it decrypts it, and then tells you whether it's in the right format or not. So JSON, right? It'll tell you, is this valid JSON, for instance. Compression oracles, and you know, there's I don't want to get into every single one of these. I will get into some of them because that's what we're going to talk about now. But yeah, so you might think there's no system in the world that's going to take encrypted data and decrypt it and hand it back to me. Well, you'd be wrong. People actually make this mistake. And it's more common than you might imagine. So, for instance, one thing I see a lot is people will have arbitrary URL redirect problems, where they'll have a website where you can give it a URL, and then it'll just send the browser off to that URL no matter what URL you give it. Now, some people think, aha, I will encrypt the URLs, and then nobody will be able to mess with them. And they have not heard my PSA, because they wouldn't do that if they heard my PSA. They would sign it instead, and that would actually be effective. But no, they encrypt it. So think about this. You can't make a system like this without actually revealing the URL, because at some point you need to redirect the browser, and how is the browser going to redirect to the URL if you don't give them the URL? So you basically have created an endpoint where anybody can submit data and then look at the location header that the app gives them in response and just read the decrypted data out of that. Now, if you happen to use the same encryption parameters, the same algorithm, key, and everything for the passwords in your database as you use for this, and then you have like SQL injection problems too, all of a sudden I can just decrypt all those passwords, you know, thanks to your handy URL redirect script. So let's talk about the compression oracle. This one is really, really cool. This is maybe my favorite attack. Maybe. So basically, the way the compression works with a lot of algorithms, and gzip and deflate, two of the most common compression algorithms, are included in this. So basically, the more repetitious data is, the better it compresses. So if you give input to something and it adds secret data onto the end of it, just concatenates that with secret data, and then compresses it and encrypts it, and gives you the encrypted version, or sends it across the wire and you're sniffing, you get the length of the encrypted data. Which means if your input and the secret data are repetitious, it will compress better. So you can see here that, you know, just getting the length of these, you can figure out what the secret might be. So imagine, if you will, this slightly contrived scenario. And you can imagine a slightly less contrived scenario, but this one is pretty straightforward. So let's say that you have a message which says the secret password is blah, your name is blah, but blah is the second blah. I should probably, okay. You get to put input in with a secret password, and you know that the format is the secret password is something, your name is whatever you put in. So you start out with you know, just one character, and you change that character. You start out by putting your name in as the secret password is some character, and you try every character until you get the version of that message which is one character shorter, because the compression algorithm was able to say, okay, these two strings are the same. Let's neutralize those. Oh, here's one where there's one more character that's the same. We'll neutralize those, so it compresses just one character better. So when it compresses one character better, you know you've got the right character there. And so you can keep brute forcing one character at a time until you have the entire secret. So cool. This is actually exactly how the crime attack on TLS works. So now you actually understand an attack that broke TLS in like, what, 2014? So yeah, don't be scared. Ain't that scary. So here's the compression oracle. Pretty cool. the padding oracle. So if you can understand this, that's great. This is the most complicated thing we're going to talk about, and we've built up to this point. We've talked about a lot of things that you need to understand how this works. So if you got everything up to this point, you got all the building blocks. So let's put them together. So with a padding oracle, you provide encrypted input, it decrypts that input, and then it tells you, is the padding that's been applied to this message after decryption, is the padding right? Now, we haven't talked about padding yet, but we're about to. This, with CBC, allows decryption and, in some cases, encryption as well. So that's pretty cool. Let's see how that works. But first, let's talk about a really common padding scheme called PKCS number 7. This is also referred to as PKCS number 5, but in number 7, they basically said, you know, this can be true for any block size. In PKS 5, they said 8-byte block size. PKS 7, it's not specified. You can have any block size, but it basically works the same way. However many blocks you need to reach the next block boundary, you add that many bytes, and their value is the number of bytes that you need. So it's ASCII value, rather. So, you know, 7 sevens or 5 fives, or if you have a piece of data that fits evenly into blocks, you add 16 16s. This assumes a 16-byte block size. So hopefully that makes sense. So in this series of slides, I like that you guys got the reference. The orange tables are failed because they generate a bad padding response, and the blue is good padding, right? So we start out with an IV. So the IV is at the top of each of these tables, and the one single block of ciphertext after decryption and after XORing with the IV produces what you see on the bottom of each table. Okay, so hope that all makes sense. So we start out with an IV of yellow submarine because that fits nicely into 16 blocks. We have a padding of hex 4, hex 4, hex 4, hex 4, and then we change to yellow submarined, which produces 4445, which is not valid PKCS 7 padding. So we try different bytes and different bytes and different bytes for the last one until we get a 1. Now, hex 1 at the end of any message is always PKCS 7 padded correctly. So now we can do a little bit of XORing. So before we do the XOR with the IV to reach the final decrypted value for any block, or with a previous block of ciphertext. So after the decryption and before the XOR step, we have something called the intermediate value. Now, if we can calculate this value, we can change the IV or block of ciphertext or whatever it is to reach exactly the value we want for any given byte. Now, we can also use this to calculate the original if we have the intermediate value and the IV. So basically, the original IV byte, the original plaintext byte that corresponds to that, and then the modified, modified IV byte. If you XOR all those together, you get the modified plaintext byte. So we know 3 of these 4 values. We know the original IV byte. We know the modified IV byte that produced hex 1 because it's good padding. So we XOR those 3 together and we get hex 4, the original value of that byte. Hooray! We decrypted a byte. But it's not that valuable to decrypt a single byte because you just get 1 byte. What about the other ones? Well, now that we know all of these values, we can control this last byte and change it to hex 2. And then we can flip the second to last byte until we get good padding. And that tells us that the second to last byte is hex 2. Because if we've set the last byte to be hex 2 upon decryption, the only thing that's going to be valid padding here is hex 2 at the end. And we can repeat this process over and over again until we've decrypted the entire block. And then we can swap out another block for the last block, or just simply truncate the last block, and do this process over again for every single block. And so we can decrypt entire messages this way. And there's a cool little technique for inverting this as well, but we won't get into it because it's a whole nother thing. There's actually no exercise, sorry. Don't have time for that. So a little bit of scary math. I'm going to mention this but not get into the details. There's also padding oracles that work against RSA, but RSA is entirely number theory based. So yeah, we start to get into heavy math there. But there's tools that'll help you do that. So again, FeatherDuster and Cryptanalib have padding oracle capabilities. There's a tool called Poracle, which helps. You might have heard of PadBuster before if you've done any stuff with crypto before. And then Rupture is a framework for exploiting breach, which is the compression oracle that works on HTTP responses and still kind of works because it's more based on the web apps than the actual, protocol itself. So let's talk about ciphertext reuse. So in a lot of cases, you can just take ciphertext and reuse it in the same context or in different contexts and get interesting results. So the replay attack is the simplest one to understand. And this is very easy to explain. You just capture some encrypted data and send it to the same exact endpoint over again. And unless there's some special unique value that prevents this, it'll work. So this attack is pretty simple to understand. So this slide is a little bear. And this is a little bear. So replay attacks can work even if you have a lot of things that you might think would stop it. So static authenticators like a password. This won't work because if it's in the encrypted data to begin with, when you send it again, you'll get the right password. So that doesn't work. Timestamps only really work if you're checking those timestamps, if you're restricting to a certain amount of time. But even then, it's usually just, hey, you can replay once or twice, right, because of the time window. And that might be enough, right? Like if you get somebody to pay you $100 and then you can get them to pay you $100 like 5 more times, well, that's not good. Unless you're, the person making this attack, in which case it's great for you. Cryptographic signatures. That doesn't really stop it because, you're replaying the signature as well. So unless you have some unique value, by the way, multi-factor authentication suffers from the same problem as timestamps because it's basically a mutated form of a timestamp. So anyway, cross-context replay attacks. This one is great. So I want to tell you a little story about a web application that I assessed that was using crypto everywhere. They weren't signing anything, but if they had, it wouldn't have helped. They just encrypted every piece of input they possibly could. So anytime they generated a link within the user interface, it would have all of the parameters individually encrypted, and it would decrypt before using any of these values. Now, I ended up finding that there was an endpoint which was like, let's call it search.php. And if you clicked to go to the next page, it would bring up page equals whatever, right? And it was very easy to infer that, okay, this is page 2. And then I could even flip back to page 1 and see page equals some encrypted blob. And I thought to myself, well, this must be the encrypted version of the number 1. So when I came across another endpoint that was like, change password.php, user ID equals some encrypted blob, I copied the page number that was just the encrypted number 1, stuck it in where the user ID was supposed to go, and all of a sudden I could change the admin's password. So that's funny. Something similar here. If you keep track of state in your forgot password mechanism for your website, and you have like a JSON blob, and then in the login system, the authentication will just make a JSON blob with the username key set to have the value of whatever username you're logged in as. You can just use this forgot state password blob. Words, it's difficult. If you take either of these JSON blobs and say, what's the value for the key username? Well, you're going to get admin. So one of these is a lot easier to generate than the other. So cut and paste attacks are a form of replay attack which just involves taking parts of different ciphertexts and putting them together. This works particularly well in ECB. So imagine a system where you have user equals something, right? And that something is whatever user you're logged in as. So you want to be admin, so you create two users, ADMXX and XXXIN. And then you take the right blocks out of those, put them together, and now you have the authentication token for the admin. So again, like I said, don't use ECB if you take one thing away. Reflection attacks. These are fun. Sometimes the system is such that you can actually get different parties to authenticate for you, to prove some possession of key material that you don't actually have. So NTLM suffers from this. It used to be possible to launch a reflection attack with NTLM, and they fixed that. This, just for the ease of explanation, works slightly differently. So in this scheme, you provide numbers with somebody to whom you'd like to authenticate, and then they are required, each party is required to sign that number with some secret key that you share to prove that you are who you say you are, because who else would have that key? So in this case, the blue and the orange represent two different connections. So you connect and say, hey, I'd like to authenticate, sign this number for me, please. And then you get the number that they respond with. You don't really care about that. And they say, sign this number. So you take that number, make a separate connection, and say, hey, sign this number that I just made up. It's totally random, I promise. They respond with the signed version of it, which you just conveniently need for your first connection. And then you go back to the first connection and say, hey, I signed that number for you. It's totally me who did that. Now run this command, right? So let's talk about the relay attack. Slight variant. This still works on NTLM. If you can get somebody to connect to you and just basically man in the middle certain cryptographic authentication protocols, you can just get somebody to authenticate for you and then drop the connection as soon as you get to the point where you're authenticated, right? So there's some tools out there for doing this sort of attack on NTLM, but most of the time this is so protocol specific that you'd have individual tools. I think it would be kind of hard to have a generic tool that does that in all possible cases. Okay, so we got about 15 minutes left and 2 sections to go through. I think I might be the last talk. Can somebody, yeah? Okay, cool. So, all right. So, poor randomness. So, this bites a lot of people. If you have a pseudorandom number generator that you're using and you have some predictable seed, like you seed based on the current time, this is really bad. People make this mistake all the time. And if you want to know just how practical these attacks are when you're talking about using micro time or milli time, you should check out, it's on YouTube. There's this guy, Chris Anley, who some of you may have heard of before. He's kind of a big deal. He does this talk at OWASP London called Telling the Time, which is great. Highly recommend it. Anyway, timestamps are not very good. You might also have a static seed, which is really bad because it means you're going to generate the same random numbers every single time. And if the security of your system requires random numbers, which many cryptographic protocols do, and even non-crypto related things, you know, that's no good. So, yeah, again, no exercise. There's a sort of like a training class version of this which has exercises, but we won't be doing those. So, depending on what you're using these random numbers for, it can be kind of bad to really bad. So, you know, we talked about if you are just feeding this random value to a pseudorandom number generator, you'll get identical bytes if you use the same value over and over again. With CBC, if you choose the initialization vector as the same thing over and over again, what you're going to have is a situation where as long as the beginning of a message is the same, up to the first block where it changes, you will see the same blocks in the same order. And this can reveal patterns between messages. So, for instance, I was looking at, just last week, I was assessing a point of sale system where they were storing encrypted usernames and passwords, but the username was easy to find out, and I saw that for several users, the encrypted username and the encrypted password were the same value. So it was pretty easy to figure out the password at that point. And even if it hadn't been exactly the same, it would have been the same up to the first 8 characters or 16 characters or whatever the block size is. So with a stream cipher, we talked about this earlier. This allows for recovery of plain text. And with DSA and its elliptic curve related cousin, this actually is really incredibly bad. Just one reused nonce allows for recovery of the private key with like a very simple operation, no brute force required. It's just like basically algebra at that point. And this allowed the fail overflow team to recover the code signing key for the PlayStation 3. So that's pretty cool. Now, you might have a seed that's chosen using a strong source of randomness, but then you only output a very small number of bits. If you're only generating numbers, between 1 and 1,000, it might be feasible to just brute force through all possible values. So, for example, the Debian PRNG bug from I want to say back in around 2006, 2007, 2008, they cut out some of the sources that they were using to feed their pseudorandom number generator for things like SSH keys. And so it's still, there's still old Debian systems out there where if you have public key-based authentication, you might be able to tell that, hey, this server, has, like, you have this public key that corresponds to one of the, like, 65,000 different key pairs that you could have generated with this buggy Debian system. So that's no good. There's some really bad pseudorandom number generators out there where it's just not suitable for cryptographic usage. But people use these things anyway. I don't want to go too much into this, but here's a non-comprehensive list. Anywho, so there's a tool called Prangster. In a lot of cases with these really bad PRNGs, with a tool like Prangster, you can actually feed some sequence of random numbers to Prangster and say, I want to know what the next one is. And with something like libcrand, for instance, if you can get like a 32-bit number out of libcrand, you can feed it to Prangster or something else, and it'll tell you exactly what the next one is going to be, and the one after that, and the one after that, because well, I don't want to get too much into it, but it's really cool, and you should check it out. FeatherDuster also has some capabilities in this space, but yeah, moving on. So, I've got about 9 minutes left. I think we can get through this comfortably. So, hash algorithms. So, how many of you have cracked a hash before? Hey, cool. All right, great. So this might be a little bit familiar. Hashes are one-way function. For those who are not terribly familiar with hashes, basically you've got this algorithm, you put something in and it spits out a fixed length code. No matter how long the data is, you still get this fixed length code. And it's mathematically impossible to invert, but you can put a whole bunch of stuff through it, and if you ever get that same code, you know what went into it in the first place. And this is how password cracking works. And some people think that, hey, if I just MD5 it twice, then somebody's going to have to crack an MD5 hash that's an MD5 hash, and that's way too complicated. But you can just write a custom hash cracker really quick that just does double MD5 on every password instead of trying to crack an MD5 hash of an MD5 hash. So goofy hash constructions only provide enough. It's security by obscurity. If you know what their construction is, it's not meaningfully stronger. Then you have pass the hash. These guys are getting all my jokes. I love it. So pass the hash is a problem where you're trading one authenticator for another. You make this mistake when designing your crypto system where you say, I don't want passwords to be exposed across the wire, so what I'm going to do is I'm going to hash them and then send them. But the problem with that is now the password isn't the password is the hash of the password. So if you capture the hash of the password, you can just pass the hash, right? So it's, like I say here, it's a form of replay attack. This has been a problem in NTLM. Cold Fusion makes this mistake, and lots and lots and lots of web apps make this same mistake. So it doesn't really help. So I want to talk a little bit about how hash functions, some hash functions, more popular ones, are constructed. So we'll abstract it a little bit, but this is a construction called Merkle-Damgard, based off of its two creators, Ralph Merkle and Damgard, whose name I totally know. So basically, you start with an initial value, you start with an initial state, and then you take each block of data, you split your data that you're going to hash up into chunks, block-sized chunks, and you mix that into the state, which begins with initial value. You mix that in with some compression function. So you take those two blocks and squeeze them together, and you throw away some data because you don't really need to keep it, you just need to make a representation, right? And you do this for every block. You squeeze it in with a compression function, and you change the state, you permute the state, and then once you reach the last part, once you reach the last block, if you need to pad it out to reach the end of a block, much like you do with a block cipher, you do so, compress it in, and then the state after that last compression function, that is the hash. So the internal state of the hash function at the time when it's finished processing all the data is the hash. Now what this means for us is that if we have some sort of signing construction that we've made ourselves, which is like take a secret value, some long password that no one will ever guess, and then add on some piece of data like, let's say, a file path. And this was actually what Flickr decided to do a while back, and then they paid out a bug bounty because they did this. Pretty cool. They took this long secret value, concatenated on a file path that they had already decided was okay, and then they tell the user, okay, here's the file path, and here's the hash with our silly signing construction. Now, the problem with this is that we can do what's called a hash length extension attack. Since the details of something like SHA-1 are known to everybody, we can say that what we can do is we can take this hash and start doing more Merkle-Damgard and use it as the initial value, because we know what the state is at the end of processing, all the data plus padding. So if we then say, all right, let's take the state at that point and use that instead of the initial value that we usually use for SHA-1, we'll just take our extra blocks of data and compress those in. And then we'll have the same value that we would get if we had just hashed under this construction the original data, the padding, and then the extra data and some more padding. So this is pretty cool, right? And so what the person who cashed in on this bug bounty was able to do was to append on like //////Etsy password some length padding and then calculate a valid hash for it. So pretty cool. So John the Ripper, great hash cracker. Y'all probably have your own preferred hash crackers and preferred language in which you'd write your own custom hash cracker. It's not that hard an exercise. I recommend it. There's a tool that I recommend called Hash Extender, which allows you to simplify the process of launching length extension attacks against Merkle-Damgard based hashes. And there's a bunch of popular ones. So MD5 is based on Merkle-Damgard. In fact, all of the message digest functions are MD2, MD4, MD5. And then you have SHA-1, SHA-256, I think SHA-512, but I'm not sure on that one. But several members of the SHA family also use Merkle-Damgard. Whirlpool uses Merkle-Damgard. I've never actually seen anyone use Whirlpool, but I know that it's also Merkle-Damgard based. So we're right up on 3 p.m. here. So I guess I took twice the time that I was supposed to. So I hope it was worth it. And do I have time for questions? Or should we? Yeah, okay. So does anybody have any questions? If you have questions or think you might have questions, you can also just take down my email and email me later. Okay, so it looks like nobody has questions. Thank you for coming.
probably